everybody. Okay, we have 2 minutes. Good morning, good afternoon before the start. Everybody, wherever you may be. I hope we need to test the screen sharing of 4 speakers who haven't arrived yet. So maybe that won't happen. And so much as say very few words. Fantastically. Thanks. So look, sorry, I've just come over from the other session. Welcome, everybody, very much. We'll get started first on time. At GW1, we do have only 2 speakers for gravitational sessions, so we have a little bit more flexibility than in some other cases. I just wanted to welcome. The session will have 3 different topics. Firstly, continuous the talks are then in the broad area of gravitational wave data analysis and sort of the technical characterization. And as I said, when we begin at 2:30 sharp, please don't hesitate to, if I could ask everybody to questions or comments, turn off into the chat box microphones during the talk or at the end. So and also please don't hesitate to raise your hand alone on the screen. Any questions and for the speakers. If you have any comments yesterday, I had to remind everybody chat GW1. If you have any questions, must stay on time. Raise your hand. This session is a little bit and I guess we'll get started. Andres, please. Before we begin, I want to thank you very much. Sincere request done and do stick to the time. We have session very strict while I was on the time because it's online. So every speaker has got 5 minutes to share your screen, whether they're invited or not. I'll be speaking about when your slot search for slides. We will have to cut it short and move on to the next speaker. And I apologise for the sort of draconian
right. So can you see my screen?
But online, thank you very much. Makes it essential.
Okay.
Okay. By my clock, it is 2:30. So it's my great pleasure
everyone.
to introduce.
Thank you for being here. I'm Andres Vargas
2
from the
speakers.
University of Melbourne.
Talk
today I'll be talking
by
about
Lily
search for
and
gravitational waves from Scorpio 6-1,
be delivered by
the third observing round of the LHC. This is on behalf of the LIGO Virgo and Kagra collaboration. So the talk will be divided into 3 parts.
So can you all see
First, I'll go through a very
now?
brief introduction, which by this point I assume you all will know very well.
I guess, yes. So
I'll go
start.
through the pipelines we're using
First,
for this search.
thank you very much for the
finally,
organizers
I'll
for
show some
inviting me
results
to give this joint talk with Dr. Maria
Right.
Essendra
So
Papa
gravitational
on this
waves are
topic of
ripples in
recent
space-time
searches for
generated by
continuous
accelerated
gravitational
masses.
waves
They
and
offer a new
implications.
avenue to study
I'll
the
thank
universe,
Maria
which is
Essendra for
complementary to
co-authoring the whole
spectra.
presentation.
We have
I'll be
already
presenting,
detected a
but
type
in
of
the
them,
end, Dr. Maria
we're
Essendra Papa
interested
and myself
in the
will
continuous
answer your
gravitational
questions
waves
together.
for this search, or CW for short.
The outline
as
of the
their
talk
name
is mainly
suggests,
2
these
parts.
are
I'll start with
waves
a
that are
brief
continually
overview
being
of
emitted
continuous
by a
wave
source, and
sources,
also
and then I'll tell you
there might
about
be
some
many
recent
channels
studies
for this
and
to
highlight
happen.
the results
A simple
from
one is
both
just
the
to
LIGO
consider a
Virgo
bump in the
Kagra
neutron star,
collaboration
and
in the
this
latest
will
run, as well
be
as from
dragging
Albert
space-time with
Einstein
it as
Institute
star goes
and
around.
other groups
The
using
thing
the
with them
open
is
data.
that the gravitational
So
waves
there
are
are
being
mainly
emitted
4
at a
types of
multiple of the
gravitational
star's spin
waves.
frequency.
On
So
the
if
short
you know the
duration
star's spin
side, we
frequency,
have
you
the
know
chirp
where to
signal
search.
from the
And
compact
well, there
binary
are
coalescences,
many
the
good
CBC
sources for
signal.
them. For instance,
We have the
yesterday we
burst
saw
signals from events like
one
supernovae.
about supernovae
On the long
remnants by
duration
Lucy
side,
Strang.
we
There's
have
also
the
low
stochastic background
mass
signals
X-ray
from
binaries
unresolved
from Scorpio
astrophysical
6-1 is part
sources
of
and
that
continuous
family,
waves from
well,
spinning neutron
many
stars.
more.
So far we have only
in
observed
general,
the first
low-mass
types
X-ray
of
binaries
signals,
such as
and in this talk,
Scorpio 6-1
we
are
will
binary
mainly
systems
focus on
composed by a
continuous
donor, which
gravitational
spreads
waves.
matter onto its companion, which is generally a
So
compact
there are
object.
a few mechanisms
And
generating continuous waves. First,
the thing is that
the
if we believe
non-axisymmetric
that
deformation due
gravitational
to
waves
elastic
are
stress
the
or magnetic
mechanism
field
to spin
in a
down
neutron star
these sorts of
can
systems,
produce
then
such little
we can show
bump
that the strain of these
on the star.
gravitational waves
So as the star
is
rotates,
proportional
it
to
will
the square root of
continuously
the X-ray
generate
flux,
weak emissions
and
of the
therefore
continuous
Scorpio
waves.
6-1, which is
The
the
wave
brightest
frequency
element
would
XP
be
in
roughly
X-rays,
twice the
will
spin
be an
frequency of the
ideal
star,
candidate to search.
and the signal
The
amplitude
thing
can be
is that
estimated in this way.
we
We
don't
have the
know
constants here. That's the principal
the
moment
spin
of
frequency
inertia.
of Scorpio
That's the
6-1,
wave
so if
frequency,
we want
and
to
d
search
is
for
the
it, we will
distance
have to go through
between Earth and Source.
broadband, and these
And the ellipticity
obviously will
defined
increase our
with
computational
these
costs.
3 principal
And apart
moments
from
of
this,
inertia
we
basically
know that the
indicates
spin
how
frequency
deformed
of
the star
elements
is.
Ps can wander
If we plug in
stochastically,
these fiducial
which makes the
values, you
search
can see
more
the spin
difficult. For
amplitude is
instance, for
very
Scorpio
weak
6-1, the
compared to a
timescale
typical
for this
CBC
frequency
signal. It
wandering
could be
has been
orders of
estimated to be
magnitude
around 10
weaker.
days. So this
That's
also
why
has
it's
to be
very
added to
difficult to detect continuous
our model.
waves. But on the other
well,
hand, because it's
the data we plan
persistent,
to
we can
use,
always
comes
integrate
from the
over a
LIGO
long time,
observatories in
even
the United
across a few
States.
runs
These are
to increase the
L-shaped
signal-to-noise
facilities
ratio.
where a laser is being pumped
If the
into
star is
cavities,
free processing, the
and
emission will
in
be
practice,
roughly
when a
once and
gravitational
twice
wave
the spin
passes
frequency
through
of the star.
this, it will stretch and
Another
contract the
mechanism
arms
is
and
called
then
R
create
mode.
a
The
certain
R modes are long-lasting
interference
oscillations in
pattern
the
here in
fluid
the output
interior of neutron
port,
star,
and
like
that
the
is
movie shows
the
here.
data.
So the emission will be roughly
So we plan to
4/3
use
of the spin
third observing
frequency.
run, which
Again,
started
if you see this
1st of
equation, this
April
is a very weak
2019.
signal. Alpha here stands
It's
for the R
divided into
mode
half.
amplitude.
The
And
first
we
half finishing
still
in
need
1st of
to
October
integrate over a
2018.
long
It
time
was
to look for these weak
a
signals.
month of the commission, and then it
Another
started
interesting
back in 1st
scenario
of
is
November,
in such
and it went
binary
up to
accreting
the end of
system as
March.
shown in this
It was
figure.
cut short
We
due
have
to
a
the
neutron
COVID
star
pandemic,
feeding on
but
a
still
companion
it's the
star
longest
like a
search that
white
has
dwarf.
been
And
run
the
by
deformation due to
LIGO,
matter
which is
accretion can
very
naturally
exciting. We plan
power
to use both halves
gravitational
in our
wave emission.
analysis.
It's very interesting.
So
The
now
torque
that
balance
we
theory suggests that
know
there's a
the
balance between
introduction,
the
I'll go through
accretion
the
torque that
pipelines we're
spins up the
using.
star and
So the first
gravitational
one,
wave
the
emission
Viterbi
slowing it
searches,
down. So the neutron star
that is
spins at
analyzed
a
with
roughly
Mayers.
stabilized frequency.
In this
And the
search,
emission of
the
wave would be
pipeline
roughly
considers
twice the spin
hidden or
frequency.
unobservable
Although
parameters
we
as
expect
steps of
some
a
wandering
Markov
in the
chain
spin frequency of the
related
star
to the
and the
observable
signal
states through a
frequency because of the
probability,
fluctuation in the
which
accretion
means
flow.
that we're
If we
considering
can
the
detect
gravitational
these
wave
continuous
frequencies
waves
as
from
the
neutron
hidden
stars, that
parameters.
can help us to
The
study
observable
the
states
barely
would be the data,
non-interior
and
of
we have a
neutron star
statistic that
that
links
can
these
tell
two.
us about
So the
properties of
hidden
neutron
gravitational
star,
wave frequencies track
shed
through
light
a
on the
trellis of
nuclear
log
equation of
likelihoods
state.
that come from a
We might
statistic, which
discover
I'll explain in the
new
next slide.
exotic states of
And we do
matter
this
inside
with
the
lots
neutron
of
star.
duration t drift.
If we
We choose
observe
t drift to be
electromagnetic
10
signals
days to
as well,
coincide
we
with
can
the
do multi-mass
timescale
drift
of the
studies. For
spin
example, we
wandering.
can study
And we
mass
assume that the
and magnetic
gravitational
field
wave
structure
frequency can
by
vary at
comparing
both
the
a
relative
frequency bin,
phase
which is
between the
related
two
to the
types of
inverse of
signals.
this t drift, for
We
at
can
least
test the
12
general
of those days.
relativity using the
When
long-lasting
we have all
signal,
of this set
etc.
up, we use
So these are
the
the
Terbi
conventional
algorithm to
continuous
efficiently
waves
track
from
the
neutron
highest log-like
stars.
path.
On the
They
other
follow
hand,
all
we
of these
also
assumptions,
expect
and here to
signals
the right
from
is a
more
little
exotic
diagram of
astrophysical
how it
sources
will look,
like boson clouds around
where
black holes.
where it's plotted the
Beyond
signal path
standard model
against the
theories
optimal
predict
path covered
ultralight
by the
bosons
Terbi
like
algorithm.
QCD axion, string axion.
So the
They can be
statistic we
dark
use
matter
is called the K
candidates.
statistic,
And if there
and it converts
exists
the
an
interferometer
ultralight
data
boson
into the
field
likelihood
around the
that a
curved
signal
black
is
hole,
present at a
the
frequency
field
f.
can extract
It takes into
rotational
account
energy from the black hole, as
various
in the
parameters
Penrose
of the binary
process.
system,
So if the
as the
super
drift within the
radiance
major
condition
axis,
here
the
is
orbital phase,
satisfied,
and the reference
that's basically
time,
saying
as well as the
if the
period of the
angular
orbit.
frequency of the field is smaller than the angular
How
speed
does
of
it
the
work?
black
Well,
hole's
here
horizon, so the
I
rotational
show two
energy can be
statistics.
extracted.
One is the f
And this
statistic
phenomenon
to the
is
left, which
most
takes into account
significant
Doppler
if the
motion
quantum
due
wavelength
to
of the
Earth
particle
rotation and
here
motion
is
around the
comparable
source
to
is
the black hole
barycenter.
size,
And it's really
which
good
means
when you
it
have an
will
isolated
naturally form
source.
a cavity
But
around
the
the black
data here
hole. The
used
field
comes
gets trapped,
from a
grows
binary, or mocks
exponentially,
a binary rather.
forming a
And you see
macroscopic
how the
cloud.
f statistic
And due
shows
to the huge number
a
of particles
modulation and a bit of
occupying a single
a
energy level,
forest
the
structure
emission
over
would be
here,
like roughly
which has to
monochromatic,
do with
like the
the
conventional
fact that
continuous wave
the
source.
signal is being
By looking for
doppler
these
shifted to the
signals,
motion of the
we can
binary.
probe a very
Meanwhile, the
interesting
J
parameter
statistic takes this
space
into account,
for
and I
ultralight
add
bosons,
the orbital
which
side
is
bands
largely inaccessible
appropriately,
on
and
Earth.
therefore
We
returns
might
a
detect
higher
new particles
peak,
in the
which is
universe.
very clear compared to the
So here we are
other data.
showing a plot
So
for the expected number of
this statistic
detectable
takes into
signals
account
from
the
the
orbital
population
parameters,
of isolated black holes
and
in the
these as
galaxy.
well have some
And this
uncertainty.
is
We have
plotting
to
as a
look
function of boson
in a
mass
parameter
on the
space.
order
We do
of
this
10 to the
by
minus 13
using
to
a
10 to
grid,
the minus
which
12
you
EV,
can think
because super
fishnet.
radiance is more likely
And a
to
lot of our
happen for rapidly
computational
rotating black
expense
hole,
goes
and
in
there's a
trying
relation
to go
between
through this
quantum
space,
wavelengths of the
as
particle and
the
the
number of templates we
black
have
hole
to
size.
search
So essentially
depends on
the
the
relation
frequency.
between the boson
So
mass and
the
black hole
higher the
mass.
frequency,
So
the
these
more
numbers
points in
would
this
vary
space we
depending
have to
on
search.
the black hole population
Now,
properties like
finishing this
black hole
pipeline,
mass,
I
macro
a little
spin.
bit of what
But the key takeaway message
model
here
tracker
is we expect
So
multiple
in general, we
detectable
will divide
signals
our
out
data
there, and
in
even
the
in some cases,
chunks, which are
hundreds,
each of these
thousands of them,
columns,
if the
and each column
boson
will have
exists, depending
some
on the
frequency
parameter
bins,
space.
which are these
So
boxes.
it would be very interesting
And
to
each
look
box
for
will
these
have a
signals and
number
probe
in it
these
that
parameter
comes out
space.
of the statistic.
These are the major continuous wave signals we are considering. And in the search, we also need to take into consideration the evolution and modulation of the signal. So as we show here, you can see there's some intrinsic frequency evolution coming from the astrophysical source themselves. In neutron stars, that's usually the secular spin down due to energy loss. Depending on which mechanism is dominant, that's corresponding to different breaking index n. In the case of ultralight boson clouds, usually we expect the signal to have a slowly increasing frequency. And on top of that, we have the yearly modulation due to the Earth's motion orbiting the sun, and a weaker effect on daily basis due to the Earth's rotation. So we do not only search for frequency and evolution terms of the signal, we also account for these modulations. Overall, we have three types of continuous wave searches. First is called targeting search, mainly for targets with known sky position and available ephemeras, usually the case for known pulsars. And that's the cheapest searches because we only look in a narrow band. The second type is called direct search. Those are for targets with known sky position but unknown frequency. So usually the case for neutron stars in supernova remnants, low mass accurate binaries, or boson clouds around non-black holes. That's intermediate in the sense of computing cost because we have to look in a wide band. And finally, we have the all-sky search, looking for any possible signals out there from any kind of sources in the whole sky in the full frequency band. And those are the most expensive ones. So following these three major categories, I'll tell you about some latest studies and interesting results from them. Although so far we don't have any continuous wave detection yet, but we have been probing very interesting parameter space, and we already have some interesting knowledge about those astrophysical objects.
So as I say, Tmax is a
first category, targeted search. As a routine, the LIGO-Virgo-Cabra collaboration usually search for all known pulsars falling in the most sensitive frequency band in all the observing runs. But new pulsars are being discovered all the time. So gravitational wave searches are becoming a new standard follow-up when the new pulsars is discovered. And here we are showing two examples, the two discoveries led by the AEI group. And this new pulsar was discovered by analyzing the data with Einstein's home computing system, and the continuous wave searches were like part of the follow-up procedure in these discoveries using the very precise radial timing solution. And especially in the future, if we do observe continuous wave associated with these pulsars, that will really open a new window for multi-message pulsar astronomy. So in the latest observing run, the LVK collaboration carried out a few interesting targeted search. So I'll give a brief overview here. One interesting search is we targeted at 5 radio pulsars, 2 recycled millisecond pulsars, 1 mild recycled pulsar, and 2 young pulsars, Crab and Vela. Since we have the ephemeras, we first assume there's a tight coupling between the gravitational wave and EM signal phase evolution. So we look in the first 3 observing run up to the first half of 03, 03A, and we obtained a constraint on the star spiriticity. So here I'm showing one example for this particular millisecond pulsar. This shaded region stands for the posterior distribution on the mass cortical moment, or the corresponding star spiriticity on the top. And you see this black line here stands for the spin down limit, which means that's the maximum ellipticity if we assume all the rotational energy loss is converted into gravitational waves. But you know, that's not usually the case because there are other mechanisms for pulsar to spin down, like magnetic dipole radiation. So this is really an upper limit. And these curves are the 95% credible upper limit set by 3 of our analysis. And this is our first time to probe down below the spin down limit for recycled millisecond pulsar. And they usually are expected to have a very low ellipticity, and you can see the limit is below 10⁻⁸, which means the equator of the star is nearly a perfect circle. In addition to that, we also relaxed the assumption here and allow the gravitational wave frequency to vary from the EM expectation. We also obtain very interesting constraint in the narrowband search, but I'll skip the details here.
Torque balance, which is
the second interesting target search is for this special energetic young X-ray pulsar J0577. It's very interesting because it's showing the largest spin down luminosity and it's undergoing quite frequent and strong glitches. Since 2017, the X-ray telescope NICER has been monitoring this object. So we use the very precise NICER data to do the targeted search for this object at both once and twice the spin frequency. And we obtained the posterior distribution on the star's electricity as shown here. The two colors stand for the two assumptions of the source orientation. And these are the 95% credible limit. And you can see this is our first time to reach below the spin down limit for this star by even more than a factor of 2. And that can be interpreted as the gravitational wave radiation due to mass quadrupole tutu mode can account for at most 14% of the rotational energy loss of this star.
Are there any questions
so that's pretty interesting. But considering there are other mechanisms for this star to spin down quite significantly, we carried out a different analysis still for this target, but for R modes. So this star glitches quite often. The data in between the glitch suggests that for some time period, the breaking index is close to 7, which indicates the R mode oscillation might be playing an interesting role. So we still use the NICER data, but we look in a different frequency band corresponding to the R mode emission. So we obtained pretty good constraint on R mode amplitude as shown here. The vertical axis is the R mode amplitude and the horizontal axis are the frequency we search. The left and right plots stand for the stiffest and softest equation of state considered. And the dashed curve are the spin down limit and the shaded region are the constraint we obtained from these two different analyses. Generally, you can see in both cases, we have probed below the spin down limit. And that's very interesting results for this target. And from this analysis, we know this pulsar is not likely to be a high mass neutron star emitting gravitational waves due to R modes.
Okay.
Regarding R modes searches, there's another interesting study targeting at crab pulsar using the open data by a group in Texas Tech University.
A few more minutes,
they looked at the first and second observing run. O2 data were divided into two halves because crab glitched roughly halfway.
Well, thank you very much.
So
again,
the upper limit on R mode amplitude are plotted here as a function of frequency. The three colors stand for the three data sets. And these are the first set of R mode constraint on crab pulsar. And it reached below the spin down limit by an order of magnitude in strength. So that's pretty interesting. Although this level of constraint is generally higher than one would expect for R mode saturation amplitude. But
thanks,
again,
Andrew. Can you hear me?
Very interesting result, and we expect that we will see better results in the future.
Yeah, feel free to cut in.
Now I'll move on to the second type of search, so-called direct research. I remind you that in these searches, we don't have ephemeras, we have to search
here. I'm going to talk
for
about
band, and that's
discriminating between a gravitational wave background and correlated magnetic noise.
In the latest run, the LBK collaboration searched for 15 young supernova remnants in this frequency band.
So when we talk about stochastic background, we're talking about something that is long duration,
interesting
and the signal
they haven't
is
spent
poorly
a lot of time
modeled.
settling down, and
Whereas,
the
for example, by
non-asymmetry
contrast,
introduced at
something
their
like
birth
CBCs would
have
be
not been
short
smoothed
duration
out,
of
so the
over
emission
minutes
could be
and
stronger.
very well modeled, so
But
that
on
you
the other
have,
hand,
you
it's
have
also
something that you can
difficult
use
to
for
search
matched
for these
filtering.
sources
The
because
stochastic background
they
is
might
persistent,
be undergoing quite rapid phase evolution.
But very
In this
poorly
latest
modeled
analysis,
and is
we
assumed to be
used
essentially
3 different methods based on
colored
different
Gaussian
signal
noise.
models. In particular,
so there are two broad
considered
categories
some
when we
new
talk
signal
about the
models
gravitational
like
wave background.
string wandering
We
coming
talk
from the
about sort
timing
of
noise
broadband
in the
persistent
neutron star,
gravitational wave
and
signal
we
whose
consider the
waveform
possibility that
sort
the
of by its very
emission could
nature
be
is not
at both
deterministic,
once
and
and
that would be
twice the
something on the
spin
right
frequency
here
of
that
the
looks,
star,
you know,
because
sort of
the
like
star could be
Gaussian noise, and that would be something like
possessing, or
gravitational wave
even
background
if
from
it's
the
not
early
possessing,
universe or
there's extra
inflationary models.
contribution from the
But you could also have a
interior of the
collection
star.
of deterministic signals
So
that are
I'll
not
skip
individually
explaining the
resolvable,
detail of the result
and that would be
here
like
because you
something
will
of
hear a
binary
dedicated
neutron
talk
stars
by
or binary
Lucy
black
Strong
holes
right
that are
after
too far
this.
away
But
to
I'll
be
give a
individually resolvable.
high-level
And so
summary
you could
here,
imagine,
showing
say,
some
this
example
plot down
plots
here being sort of
showing
swamped
the
by
upper
noise,
limit on
and the cyan, which
intensity
is
of
the
the
binary
star,
neutron
and
stars,
mode
and the
amplitude as
purple,
a
which are the
function
binary
of
black holes, sort
frequency
of
from
popping
3
off
out
every
of
once
the
in a while
15
and giving
targets
you a burst, but you
coming
can't
from one
necessarily see
method.
them individually.
But the
And
takeaway
so their
message is that
superposition
we
gives you
have
some sort of
reached a very
background hum
interesting
that
level
adds up to
of
something that is
ellipticity
effectively
below
Gaussian.
10 to the minus 6
You could
and
also have
mode
other
amplitude
potential
below 10 to the
unresolved
minus 3 at many
examples,
frequencies. And
but
those
binary
are the
systems
interesting
are what we
level
expect to
predicted in
dominate
theory.
and probably and
Okay,
almost
so
certainly
for the
dominate
same type of
any sort of
targets
early
beyond
universe models
supernova
as well.
remnants, there's an alternative approach
So the
which
stochastic
can
background is usually
concentrate
characterized by the
efforts and
dimensionless energy
computing
density,
cost
which is
on
the
a
energy
few
density in gravitational
promising
waves
targets and search as
per
deep as
logarithmic
possible,
frequency band, which is why
instead
we
of
have this
looking
F
for
over
many
df,
of them. And
normalized
that's
by the
usually
critical
an
energy
approach
density to
taken
close the
by the
universe.
AEI group in the past years.
Sort of similarly to
And
a
the
lot of
group
the
has designed
cosmological
an
parameters that you might see.
optimization procedure
And
to
this is often
select the
characterized
most
by a power
promising
law,
targets based on
where you
their
have some
age, their
amplitude of the
distance,
stochastic background at
the
some reference frequency,
astrophysical
so the
prior of
amplitude is omega at some
frequency and
reference
other
frequency f ref,
properties given
and you
a
have the sum
fixed
power law with the
computing
spectral
budget.
index alpha.
And this
And alpha
procedure
is equal to
identified that
2/3
these
for
3
gravitational wave
targets are
background
worth the
dominated by
investment.
unresolved
Vela
binary
Junior,
in
Cas A,
spirals,
and
like from binary neutron
G347.
stars or binary
So the
black holes,
searches were carried out
which is
using
what we
Einstein
expect
home
to
computing
dominate
system
our background. And
on LIGO open
there was a
data.
talk yesterday by
No
Mary
detection was
Sakalaria
made. One
in
signal
the
candidate
Gravitational
was
Wave Sources Block
identified,
1
but
session
eventually not confirmed
that goes
in
through this
follow-up
in quite a bit
analysis,
of detail,
including
the sorts of
looking
physics
in
and
the
things that
EM
you can
data
constrain
and
using
the
the
latest
stochastic background.
analysis within LBK using the
And the way that we
latest
search for these
data.
things, because there's
But
not a
anyway,
well-defined signal
these deep
for the
searches
stochastic background, is that we
yield
cross-correlate data
very
between different
sensitive
detectors,
results,
so we can construct
showing
this
as this
C hat
up
of
limit
F,
on the
where
signal
S1 and
amplitude in
S2
these black
are
curves.
the Fourier transforms of the data
And
streams
for
in
these
detectors
2
1 and 2,
objects, these
and it's
remain the
normalized by
most
tau, which is
stringent
the time over
constraint
which those
to
Fourier
date.
transforms are taken.
So that's that's
And
pretty
you can take the
interesting
data from
results.
S1 and you can write it as a
And
sum of some
here we
gravitational wave
also show
signal
the latest
and
result
some
from
noise in the
LBK,
detector.
but these are coming from a different
And
signal
now you
model,
can
basically
substitute this
considering
in,
spin wandering.
and
So
you can
there's
take an
also
ensemble
a
average, and you
balance
can
here
get this sort of
between the
list of
sensitivity
two-point
and
functions here.
flexibility of
And
signal
you have
models.
something that
They are not directly
contains
comparable.
gravitational waves in this
But
first term.
these
You have
very
something that
sensitive
is noise,
results can be
correlation
converted
between
into
noise
the
and
upper limit
gravitational waves
on the
in
star
the second and third terms,
specificity
which should go to
as shown
0.
here.
And
So
you have
this
some
set
term
of
that looks like
results from the
the
AEI
correlation of the
analysis
noise in detectors 1
set
and 2.
very interesting upper
So
limit
typically
on
what we
these
do is
2
we assume
objects
that
probing
all
below
these last
10 to
3
the
terms go
minus
to 0,
6
that the signal and noise are
ellipticity.
uncorrelated. That's something that I
Okay,
really hope is
so
true.
another very interesting target
And
for
the
direct
noise is
research is
uncorrelated
the
between the
accreting
different
binary
detectors.
system SCORE X1.
And then you have some
As I
gravitational
mentioned
wave background
earlier,
signal.
in
So if you
these
average
accreting
over many,
systems,
many times, these
there's
3
a balance
terms
between the
go
accretion
away, and
torque
you're left
and
with C hat
gravitational
converging to
radiation
something
reaction
that's
torque.
proportional
So which
directly to the
means
gravitational wave
the
background.
brighter the accretion,
But this last thing
the
is not
stronger
necessarily
the
true.
emission
The
could
noise
be.
is not
So
necessarily
SCORE
uncorrelated
X1
between the
is the
detectors. And
most
so
X-ray
we want to
luminous
know
low
at what
mass
level
X-ray
do we
binary
expect
in the
this to
sky,
break down.
making it a
And
very
in the future,
promising
if we run
continuous
into
wave
this
target.
correlated noise,
So various
how are we
searches have been
planning to
carried
deal with
out
it?
using different methods in the past.
So
And
the
here we're
correlated
showing
noise that
a
I'm going to
latest
speak about
study
today
from the
is
AEI group
correlated noise
using the
from
LIGO
sort of
O2
globally
data,
coherent
and
magnetic
that's
fields.
based on
I have an
an
extra
improved
slide on
method
some
with
other
better
potential
efficiency
correlated
here.
noise that comes
So
up
the
in our
results are
detectors.
shown in this plot.
If you
These
want
are the upper
to
limit
hear about that. But in this case, we're going to talk about Schumann resonances, which are the sort of the eigenmodes of the Earth ionosphere resonant cavity. So they're excited by lightning strikes all over the Earth. And what you get are peaks in the magnetic spectrum at say 8 hertz, 14 hertz, 21 hertz, 26 hertz, going up the band. And all of these are PSDs of different magnetometers all over the world. So Poland, Colorado, Argentina, LIGO Hanford, LIGO Livingston, so on and so forth. And so you can see that first there's a variation in these peaks, but these peaks are common to all of these spectra. And if you take a coherence between a magnetometer at LIGO Livingston, which is
example, like
LIGO1,
in this
and say
figure here,
Poland,
we are
then you
showing
see
the
a
upper limit
spike
on the
here,
magnetic
or a
field
peak
of the
here
neutron
in the same
star
place as you
as a
saw on the
function
plot
of the
above.
star's mass
So the
at
purple is
about
the correlation
170
between two
hertz for
magnetometers
these
that are
various
essentially next to
equations
each
of
other or
state.
very close to each other.
As a
The
reference,
black is
these
what you would
vector
expect
curves
the
indicate
coherence
the
here to look
various
like
fixed
if there
number
was
of
no correlation
compactness
at
of the
all
neutron
between
star.
the two signals that
And in
you're
this
calculating the
bottom
coherence
plot, we're
for.
showing
So you
the
see that we're
mass
seeing very strong
radius
coherence
relation for these
for
various
magnetometers that are
equations
separated
of
by
state.
tens of thousands of kilometers.
And this shaded region is
And this is a
excluded
problem
due
if
to
those
the
magnetic fields
measurement.
couple into our
So
detectors
you
in
will
some
hear
way. So
more details
if the
from
magnetic
Yuehao Zhang's
fields
talk
induce
about this study
somehow
and
induce some
regarding the
motion in the
updates in the
mirrors
latest
in a
O3
detector
run within the LIGO-Virgo-Cabra collaboration,
Livingston, Louisiana, and one in Italy, then the correlation between those
now let's
magnetometers
move on
or the magnetic
onto the
fields
third
will imprint
category,
themselves
the
on the
all-sky
mirrors.
search.
And when you go to
one major challenge
correlate
here
the data
is the
between
computing
those
cost.
different
It's very
detectors,
expensive.
you run the
And
risk
we have
of
to
having
choose
correlated
between
noise
the parameter space that can
and
be
biasing
covered
your
and
estimate of
the
the
best
stochastic background.
sensitivity we can reach. And the
Okay,
AI
so
group
how can
usually
these low
adopt
frequency
an
magnetic
approach
fields
to
couple into
dig
the
very
detectors?
deep.
If you have
So
some
you
sort
can
of
see there
magnets
are two
on the
major
mirrors
types
that
of
are used for
searches carried
actuation to
out
keep the
lately.
mirrors in lock,
One is the
then those magnetic
so-called
fields
Falcon search
could accidentally
that
drive
concentrate
the
on
mirrors.
low electricity objects
You could
in
also
a
have
wide frequency
electronics.
band,
You have lots and lots of
and
cables
that's
all
very
over your site.
sensitive to weak
And
signals.
if you get some
As
sort
you
of
can see here by
changing
these
magnetic
gold
field that could induce a
curves
current
that
in those
shows
cables,
the upper
and
limit
that
on
gets
the
into your
signal
feedback systems
amplitude,
and imprints
and it
itself on the
can
mirrors,
reach a very low level,
then you could
probing
run into a
below
problem.
10 to the
And
minus
so what they do is
25.
they measure the coupling
And that
function
can be converted
between the
into the
magnetic
upper
field
limit on the star's electricity here, assuming a given distance.
the actual
and
differential
you can see
arm
it
motion
can
of the
reach
LIGO detectors,
as
the
low as
strain
10 to
data that
minus
you measure
8
to do
in
your
some
searches with.
cases.
So what you have here on the y-axis of this top plot is a magnetic coupling function, so how much our mirrors move in response to a magnetic field of a certain strength, in units of Tesla, as a function of frequency. And so you can see that it looks like a broken power law generally, the general trend. So this first plot is as a function of time. These were measured essentially every week of the last year of the O3 run for LIGO Hanford and LIGO Livingston and for Virgo.
That's about
and
40
what we have here is
higher than
the strength of where this break happens.
So this is the deep searches.
The
As a
amplitude
reference,
here,
you can
we have
see the O2
first spectral
LVK
index, so
results are
roughly
slightly
-3
less sensitive than
as a
these
function
deep
of
search,
time.
but
And then we
that
also have the
covers a
second
larger
spectral
parameter
index, this
space.
turnover
So that's
as a function of
an
time
alternative
down in the bottom
approach
right as
I'll
well.
show later. So that's
So
usually
you can
the
fit these
approach
coupling
taken
functions
by
with a
the
broken power
LVK
law
collaboration
or
to
something along
search
those lines.
wide.
In the latest
but
you also
run,
have
we
some
cover a
resonances
wide
in some
parameter
places,
space, like the
which could cause
frequency band
problems
here,
in the
and
future,
also a
especially
wide spin-down band
if those get louder
from here to
or
here. So
you change your
basically,
detector
the
configuration. So
area
these are
in
all
this
things that we
light
have to keep
blue
an eye
region.
on.
And similarly,
You
we
can
search
construct a
larger
correlated
parameter
magnetic noise
space
budget.
as
So what you
indicated
can
by
do is
the
you can take
blue,
those coupling
dark blue
function
region back in
measurements from the
O2.
previous slide, and you can
And
take
the deep
coherence between
search carried out
magnetometers
by
that
the
are
AI group is
sitting next to
concentrated
the
on the purple
detectors,
region for
and
Einstein
you can
home search
multiply the
and
coupling
a narrow
functions
band
by your
for the
coherences,
Falcon search
and you can
indicated
essentially get
by
an
this
estimate
red
of the
curve. So these two
the contribution
completely
of
different
correlated
choices
magnetic
are
noise
usually complementary to
C
each
hat
other.
of F
A
or to your
wide search
estimate of
can
omega
make sure we
GW,
don't miss anything relatively
which
obvious in the
is
whole
what we're really
interesting
interested
parameter
in.
space.
So we've constructed a budget
is sensitive
for
to
the
weaker
O3 search,
signals in specialized
and that's
region.
what's in this shaded
here
region
on,
here.
on
so
the right,
the uncertainties here in
the
the
upper
shaded
limit
region,
on the
which is quite
signal
large,
amplitude as a
sort of
function of frequency.
keep
This green
encode
curve
in them
comes from
the changes
latest
in the coupling
O3
function as a
analysis
function
in the
of time over
LVK
the course of the whole
collaboration,
run.
and the magenta
The
color
red
was
is
the
the
sensitivity
sort of
back in
integrated
O2 from
sensitivity
LVK,
across the whole frequency
and
band
this cyan
of
color
the
is from the sensitive deep
of
search,
the O3
deep
search for
Falcon
gravitational
search
waves for
using
a
the O2
stochastic
data.
background. So this red should be
And
compared to the
finally, this
general
plot
trend
is showing
of
some
the black
implication we've got from
and
the
shaded
O3
regions down
LVK
here.
analysis.
And so you
It's
can see
showing
that
the
we're a
range
couple
we
of
can
orders
reach in
of
universe
magnitude
as a
below
function
our
of
sensitivity.
frequency.
So that's good news. We don't expect
These
that this
black
O3 data
curves
is
correspond to
contaminated by
different
correlated
maximum
magnetic
range
noise.
of F dot,
Up here
assuming
is
all the
the
spin down
sensitivity
is
in each
converted into
individual frequency
gravitational
band
waves.
of the search.
And these
And so
colored curves stand
this
for
could be
the
compared to, say,
different
the
elasticity
spikes
of the
that you you
star.
see
So
in
generally,
these black
larger
pieces, and you can
larger
see
spin
again
down, the emission is
that
stronger,
this is
and we
much
can
lower
reach
than
further.
these black spikes are much lower than this black curve up here. And so again, we don't even expect to see sort of sharp spectral features
deeper in the future when the detector is more sensitive.
And it looks like we don't. So that's all good news. So this is how we construct a correlated magnetic noise budget, and it looks like for O3 we're okay.
Even more
we can also do
limit level
we can also try to estimate
the chance of detecting
parameters and try to estimate the strength of the correlated noise, especially important for future detectors, which will be much more sensitive. So as this red curve gets much lower, for example.
Analysis I show in the previous page
and as I said, the current budget indicates correlated noise is not an issue, but we're interested in this for future detectors.
And also
so I'll introduce very briefly a method for simultaneously measuring correlated noise in the gravitational wave background.
Due to the binary orbit.
So you can take your C-hat-FF. This is normalized slightly differently from the one that I showed a few slides ago, but you can think of it in spirit as the same thing. And you can subtract from it some model for the stochastic background, or some model for the stochastic background plus some model for the contamination due to correlated magnetic noise. And what you should get back is, after you subtract this off, is just pure Gaussian noise should be left over.
We can reach further. So the shaded region
in this case, you can include a power law model for gravitational waves, and you can include some model for the magnetic
other
magnetic
effects like
budget.
accretion
And
might
I'll discuss this on the next
this
slide.
region.
So
as a reference,
this omega mag is going to be some product of your coupling functions or your transfer functions. The transfer functions include phase, the coupling functions that we talked about before ignore phase. And for now, we're assuming that these transfer functions are real, which is a pretty strong assumption.
We have been all talking about the studies for neutron stars.
To make the problem simpler. You multiply these by essentially your coherence or your cross correlation between
the latest study in
data
O3 is still
at your two
underway.
sites. So this is a magnetometer at site 1, this is a magnetometer at site 2, and the rest of these things are normalizations to put these in the same units as this omega mag, essentially. So this is a geometric factor, and this piece contains in it different constants
so the shaded region
and
is
also
the
weights
excluded
related to the noise in the detectors, the LIGO detectors. But these transfer functions, actually, we're going to allow for now, even though we have coupling function measurements, we're going to allow these to be power laws that have
1 kilopasecond. The different colors
variable amplitude and variable spectral index.
So basically, the signal decays over time.
I'm happy to answer why that is, but essentially it's because the coupling function measurements are quite uncertain. So we want to be able to allow those to have some,
and on the right-hand side,
change.
This is an interesting result.
And that uncertainty is built into the budget, but it wouldn't be built in necessarily out of the box to a parameter estimation method like this. So that's why we parameterize our uncertainty in this way.
And this is showing the decay constant
okay,
on
so
y-axis,
if you put in a very strong correlated magnetic noise signal and you try to estimate it back out using
so the key
parameter estimation, you can estimate the kappa for each of the different detectors for the coupling function or the transfer function for each of the different detectors. So H, L, and V, and the spectral index for each of the different detectors. And one sort of striking thing to note here is that while Virgo is in this case not particularly sensitive, and it actually doesn't help us measure gravitational waves, it does help us estimate the parameters for coupling functions in the individual detectors very well.
Quickly touch on a
and there are a couple of reasons for this, but you can see that the green is if you have only Hanford-Livingston, and the blue is if you include Virgo, and it's helping us with a coupling function with Hanford and Livingston as well. So that's good news. You can also construct a Bayes factor.
The idea is the dark photons may directly
compares
the baryons in the test
a model that includes gravitational waves and correlated noise to a model that includes only correlated noise. So essentially trying to detect gravitational waves in the presence of correlated noise.
So we can use
and you can see how that Bayes factor scales as a function of time, assuming design sensitivity for LIGO. The orange is if there's no correlated magnetic noise at all, and the blue is if you have a strong correlated magnetic noise signal. The green is if you have a strong correlated magnetic noise signal, you have very noisy measurements of your magnetic
So the red and black curves stand for the
and you can see that it will increase time to detection, but the general scaling is still linear with time, which is very good news. So it will increase time to detection, but it's not going to hurt you all that much.
Of 10 to 100.
So we did this. We actually applied this method to O3 data. We found no evidence for correlated magnetic noise
complementary
in the data.
And
we found no evidence for correlated magnetic noise or gravitational waves in the data.
I'll just give a very short
and as I said, this is not surprising.
We have been carrying out multiple types of searches for multiple types of continuous wave signals,
but it's a useful method to keep in mind for future
Many of these
detectors.
searches are computationally challenging.
We need to update our
optimal
methods for future runs, especially for parameter estimation. The parameter estimation methods don't include these potential resonances that you see, these peaks in the coupling functions. It also didn't include higher frequency coupling function measurements, which is something that a student Camille Jensen is
we
working
have been
on.
probing very interesting parameter space, and we learned a lot of properties.
And we also
neutron
would like to
stars
include multiple pairs of
even
magnetometers at
particles
separate
are there.
sites. At the moment, we're just using a single
So
pair.
the latest study,
so I'll leave the conclusions there because
bosons,
I've run
the
a little bit
direct
over,
search
but I'm
for
happy to
backfold
answer
on dark
questions
matter,
from people.
demonstrate that we can
I
even
can't see the
study
chat, so I'll let
particle
Andrew,
physics using gravitational wave detectors
field
and
questions.
continuous wave methods.
Thank you very much, Pat.
So in the future, the detector will get more sensitive, and the third generation detectors are being planned, and we are really at the door of new discovery and new physics. So let's look forward to the detection of continuous wave. Thank you very much.
I had a couple of questions.
Thank you very much,
on slide
Louis.
12.
And major thank you to Dr. Sun and Dr. Papa for
I don't seem
really
to be able to see my own slide numbers. Oh, there it is.
You're on 17.
We have time, 5 minutes
the little
for
box
questions.
is on top of it.
Please
yes,
indicate your question with a raised hand,
the peaks in the
or
black,
put it in the
black
chat
dash,
if you like.
seem to be in the same place.
Our question is Andrew Cameron.
Is that
hello? That was a very good talk. Quick question about the targeted search for continuous waves from the Crab and the Vela pulsars. Given that those pulsars are quite prone to glitches,
so some of those
when you're running that search, how do you account for the glitching behavior of those pulsars? Is it just a case of accounting for whatever glitch correction there is in the timing ephemerides, or are there other gravitational wave consequences that a glitch would have that you need to account for?
Measurements from Virgo, there were spikes in the magnetometer
yeah, that's a very
data Virgo.
Interesting question.
They're also potentially due to the fact that this is
probably
a bit,
I'll need to double check,
but
detail,
my
impression was the
essentially
period of glitches are not included in
real
these
part
analysis.
of the complex
we
cross
only
correlation
search in the data
will pass through zero
glitches,
for the magnetometer measurements in different places than it would pass for gravitational waves between the sites.
Okay, thank you.
And what that essentially means is that
thank you very much.
Your
other
let's
questions?
see if I have an equation here. That's essentially this gamma function, and this gamma function will go to zero in some
Lily,
places and make this thing blow up. And essentially, this thing will also go to zero, and it will go to zero in different places from this thing. So if these were gravitational waves,
why do we
this numerator would go to zero in the same place as the denominator,
from every direction to have a coherent oscillatory
for magnetometer data, it won't, and so you will actually get those spikes. And so it's a combination of potentially magnetic artifacts, but also sort of this sort of strange feature of the way that this model is constructed. But it's actually quite nice because it gives you actually very useful information.
Hanford and Livingston detectors should feel the same field of the dark photon, because the wavelength should be much longer
noise, hopefully not correlated.
The distance between the two detectors.
Is there
there's also a correlation between
I could imagine some sort of a scenario where when you have a signal coming in
thank you very much.
data,
okay, so they're very, very long light waves.
Has that been considered? Is that, how do you discard that possibility?
Fascinating.
Yeah, it's really funny.
Any other questions?
I've given a talk like this many times, and I've always said that, and I've always sort of thought, oh, it's not something we have to worry about. And this time, as we went by it, I thought exactly the same thing. It's not something that I've ever heard anyone talk about, but I think that probably it's not something that we would expect to see. I think it would be probably some sort of nonlinearity,
a balancing act
in
here.
the
We
control
want
loops
to keep to the time in the program.
I would not be able to understand. I think it would probably have to be a very, very loud signal.
We also don't want to go
it would probably be like a very, very loud CBC signal that would cause something like that. And I really don't think it would be something that would be a problem for a very quiet signal like the stochastic background.
No
Right.
further
I guess
questions.
the
Thank you
might help
again,
there's glitchy
Lily and
correlations.
Alessandra, for
Yeah,
an excellent presentation.
Okay, cool.
The
Thanks.
next speaker Thank you very much. Lucy. The next question is from Lucy Strang, and she will be presenting on continuous gravitational waves.
I did have two questions,
young
but
supernova
Julian stole one of them.
All right. Hi, everyone.
I guess
I will just take a moment to share my screen.
All of this correlated noise in the context of the stochastic gravitational wave background.
All right. I'm going to go ahead and assume that everyone can see
this noise for other
Yes.
gravitational wave signals, or is it simply?
So hi,
it's
everyone.
too quiet for
My
us
name
to
is
need to
Lucy
worry about
Strang,
that?
and I'm here today to present some results on behalf of
yeah,
the
so
LIGO-Virgo collaboration
this specific form
about
of
a recent
noise,
search for continuous gravitational waves from 15
yeah, so
supernova remnants
that's
using
actually
the
a very
early
good
third
question.
observing run
So
of advanced LIGO and
for
Virgo.
future detectors, actually,
So the
this
way
could
this
be a
talk is going to
problem.
work
So
is
for
I'm
Einstein
first going to
telescope,
do
for
a very
example,
brief overview of
there's a
continuous
chance
waves
that,
for the last people who snuck in the last 2 minutes.
local magnetic fields
look
will
at
be a
why
limiting
supernova
noise
remnants
source
in particular,
for
which
Einstein
supernova
telescope.
remnants we look
So
at, how we look for them,
there's a paper
and
called
the
Site
inverse
Selection
of how
for
we look
Einstein
for them, what
telescope,
pipelines we use is what physics is each pipeline sensitive to.
they sort of show the design sensitivities, and they show expected noise
astrophysical
for,
implications,
say, seismic noise
and
in
if I
local
have
magnetic
time,
fields,
I'll
and
do
they're very
quick
close
comparison
or
slide,
over
but
the
I
expected
will have a timer
or
going, so
the
I
proposed design
go
sensitivity.
over
And so for
I'm
something
running
like
short on
Einstein
time.
telescope, that's a problem, because actually
So
just
in
even
terms of
local
continuous
magnetic
gravitational
fields
waves,
will then be coherent
continuous
because you have multiple
quasi-monochromatic
interferometers
gravitational
for
waves
Einstein
are
telescope
a
in one
target
place.
for detection,
And
but we
so
haven't seen them yet.
you would
They're
probably try
expected
to do
have
some
a much
sort
lower
of online
gravitational
noise
wave
subtraction
strain than the now
and use
regularly
this.
detected
But that would be a
primary
problem for
coalescence
almost any
events,
sort of
but
searches
they're there for the
that are
full duration of the
cross-correlating data
observation
between
run.
detectors.
So by
So things
increasing
like
our
burst
observation
searches
time, we can increase the
aren't
probability of
using
detection.
waveforms, for
There's
example.
a few ways
For
you
anything that
can
does some
generate
sort of
continuous
matched
gravitational
filtering, I
waves,
think
but in this talk we're just
this
going to
specific
focus on
source would not be an
triaxial
issue.
rotating
There
neutron
are other
stars.
correlated noise sources
These will
that
produce a
could
simple
be, for
sinusoidal
example,
signal,
like
most
coherent
likely
combs
at
and things like that.
twice the spin frequency of the star.
Great, thank you.
If the stellar frequency is changing,
Very
then we can
much.
start to parameterize that by bringing in the time
We are at the end of
derivatives
the
of f
session.
dot
I
to f
might
dot,
just
etc.
sneak a very quick question in.
We look at young supernova remnants because young supernova
done
remnants
this sort of
contain
study
central compact objects, and those are likely
correlated
to be young
magnetic
neutron
noise
stars.
for
We define
LISA,
young in this search by
because
using age and
presumably
distance
the
estimates
solar
from the
wind
literature.
especially,
These can have
you
large
would expect
uncertainties,
pretty
but
strong
all that
magnetic
does is
correlations
it means we
across
might be a little
the
bit too
million
optimistic
kilometre
in a couple of
baselines that
places.
ELISA would
It doesn't affect the actual sensitivity. We're
That
interested
I
in young
don't
neutron
know
stars
about.
because
Yeah,
they're more likely to be non-axis symmetric than other isolated
I
neutron
don't know
stars.
the answer to
And we know that
that.
the gravitational wave strain H0 is proportional to the colloidal electricity.
That would be interesting, though.
They're also
Yeah,
more
like
likely
I
to be
don't know what the
rotating
noise budget
rapidly, and
looks
the
like for
gravitational
LISA
wave strain is
Pathfinder. You
proportional
would potentially
to the
expect
square
that
of
to be
frequency.
a noise source there, but
Unfortunately, we
to
don't
start
know
with,
exactly
so
what
it's
frequency
probably
these
my hunch
particular
is that if
neutron
it's not
stars are
limiting
rotating
LISA
at, so we have to
Pathfinder,
do a
then
very
it's
wide search spanning
maybe
up to a couple of kilohertz in this
not
case.
as big of a deal for making
And
sort of
we're
short
also
duration
going to
detections of
search a
things
wide
like
range
double
of
white
the
dwarfs,
first
but maybe for
frequency
longer
derivative f
duration
dot,
things, it
because
could
we
be,
expect
because
that to
again,
scale
you would
approximately
eventually run into
as
this
f to the
issue.
5,
But I
and
don't
again, we
think that
don't know
anyone
what the
has
frequency
talked
is.
about it, but I
So
could
if we
be
want to
very
search
wrong.
a large number of targets over such a wide band, we're going to
Great.
need efficient algorithms
Okay,
to do so.
well, look,
We
we
use
are at the
3
end of the
algorithms
session
in
for
this
today.
search,
Let
each
me
forming their
just
own separate little
say
search
3 quick
pipeline.
things.
The
Firstly,
first is the band
a
sample
massive
data
thank
algorithm,
you to everybody
henceforth
who
I'll
did
just
come
refer to
along.
this as the Bsd algorithm. There's the
Secondly,
single harmonic
thank you to the
Viterbi
2
algorithm,
speakers
which
for
I'll
excellent
sometimes use the
talks and for
shorthand
sticking to
SHV,
time.
and the dual harmonic
And
Viterbi algorithm.
thirdly, thank you very
All
much
3
to Liam
algorithms
Dunn,
use
who was the
the
co-host
data from the first
technology
half
working.
of the
I'll
first
just remind
observing run
everybody
of
that we've got
LIGO,
the
which I'll
next
henceforth just
GW1
refer to
session
as
on
O3A.
Thursday,
And the
starting
Bsd
at
algorithm also uses
16:30.
Virgo data,
So
but
for
that
those of
wasn't
us
going
in
to be a
Australia,
huge boost to the two
an
Viterbi
uncomfortable
algorithms, so
time,
they stuck
but
with
pretty
plain LIGO
convenient
data.
for the rest of the world.
These
So
are the targets we
I
looked
look forward
at. I'm
to
aware
seeing you all
that
there.
a large table
Bye-bye.
is impenetrable in a talk, so let's just break it down into 2 sections.
Thanks,
In the
everyone.
top half, highlighted currently in green, we have the targets that are searched by all 3 pipelines. These tend to be a little bit closer to Earth, and as far as young supernova remnants go, they're a little bit older,
Andrew,
so they're spinning down less rapidly.
Maybe you can
This means they're easier to search for, and it's easier to put a large
I
amount
think,
of computing resources
yeah,
behind them.
I think
At the lower half of the table,
maybe
we have
we
targets
just
that are a little bit further away,
run for a minute,
or we expect they're spinning around more rapidly.
and then just quit it.
Because this makes them a little bit
I had
harder
the same
to search
question
for,
actually.
we just put our most efficient algorithm after them, which is the single harmonic for Terbi algorithm.
Reply from the organisers saying yes.
In terms of the three pipelines we use, before I dive into it, I do want to define a little bit of jargon I'm going to be using on and off throughout the talk, just to make sure we're all on the same page.
Thank you,
So the most obvious way to do a search is to do what we would call a coherent search, where we have an exact matched filter search that's across the full observation time. So we guess what we think our gravitational wave signal is, we search the data for it, and if it's not there, we take our next best guess and we search, and so on and so on. And if we manage to guess the correct signal with only a few templates, this is by far the most sensitive search we could do. But if we need a lot of templates to try and find our signal, the trials factor can start to impact our sensitivity. And if the signal doesn't look the way we expect, we could be completely blind to it. This also ends up being quite expensive if you have a large number of templates or as you increase your observation time. But given a large part of the continuous wave strategy is to get longer observation times, that's a fairly large drawback. There are also semi-coherent searches. A semi-coherent search involves taking your full observation time and breaking it into little blocks of duration TCO, which stands for coherence time. As the name suggests, you would then do a little coherent search on each of your blocks and string them together. This is a very efficient method, even if you use long observation times, and depending on the algorithm you use, you can accommodate different signal models. The first pipeline we're going to discuss is the Bsd pipeline. This uses interferometer time series downsampled at 0.1 seconds, and then takes these, applies a Doppler correction, and applies a fast Fourier transform on blocks of duration TCO. This is where that semi-coherent part comes in. We then use the frequency Hoff transformation to map the results of that into the source intrinsic frequency and spin down space. And from here, we can start identifying candidates in each interferometer. None of the candidates that are coincident in Hanford, Livingston, and Virgo survive the automated veto process. There's a further roughly 10 to the 4 candidates coincident in just Hanford and Livingston, but not Virgo, and none of those survive the veto and extended follow-up process. So from the Bsd algorithm, we report 0 continuous gravitational wave candidates. The Bsd algorithm is the closest algorithm in this session to what I would call a traditional search, so it's very sensitive to the standard kind of signal. Next, we have the single harmonic Viterbi algorithm, which is based on a hidden Markov model. Here we have hidden parameters treated as links in a Markov chain and connected to an observable through some probability. In our case, that hidden true parameter is the gravitational wave frequency, and the observable is the result of our little coherent search on blocks of duration TCO. In our case, the coherent search is called the F statistic, but all we need to know for now is just that it's a coherent search. We allow our signal to wander up and down one frequency band per little block of duration TCO, which means we have a random walk signal model. This lets us track stochastic spin wandering, which is not covered by most other pipelines. And because we allowed a short coherence time in this search, it means we're able to track a very large range of spin down, up to about 10 to the minus 8 hertz per second, which I think is the largest for any of these targets searched. We identify about 9,000 candidates, none of which survive the veto and follow-up process. Lastly, we have the dual harmonic Viterbi algorithm. This is based on the same underlying hidden Markov model as the previous pipeline, but there's a different underlying physics. If we have a star that's freely precessing, or if you want something a little more exotic, you could have a superfluid interior pinned to the solid crust, then you're going to have gravitational waves emitting at both once and twice the spin frequency instead of just twice the spin frequency as is normal. If we track both of those frequency bands, we can therefore improve our sensitivity. And that's exactly what we do here using Viterbi. We use 2 separate coherence times of 9 hours and 12 hours, depending on the age of the target. And we identify about 470 candidates, none of which survive the veto and follow-up procedures. Because at this point we can say we have found no continuous gravitational wave candidates, we can start talking about sensitivity and upper limits. I'm very careful in splitting out these into 2 separate things because strictly speaking, we can only set a frequentist upper limit in a band where we've done injections. But as I mentioned, for some of these targets, we're searching over the full LIGO band. Trying to do injections into that would be, frankly, agonizing. So what we do for each individual pipeline is we choose a few random bands, set upper limits there, and then use those results to infer the sensitivity in the full band. So let's use the Bsd algorithm to have a bit of a closer look at how that works. So we can see on the right-hand side, there is this lovely plot for G65.7 plus 1.2. And we have these red, purple, and brown crosses corresponding to the 95% upper confidence limits in the Livingston, Hanford, and Virgo detectors, respectively. These were each obtained by injecting a set of signals at different strains and attempting to recover them. When we managed to recover 95% of the signals, we were able to say that that was our 95% confidence limit. To get the blue, orange, and green dots, which correspond to the sensitivity for each of those detectors, we simply do a piecewise linear extrapolation between each of those upper limits. We can see here that for each detector, we actually managed to get below the age-based limit on what the gravitational wave strain could be, which means we're starting to actually probe the underlying physics model that could generate these continuous waves. The Bsd algorithm has our lowest confidence limits in this search and manages to get as low as 7.8 times 10 to the minus 26 in the Livingston detector. Next up, we have the single harmonic Viterbi algorithm. In terms of how we set these limits, it's a very similar process. We choose a set of random bands, we do injections, and these give us the results in the panel on the right, where we have these orange crosses. We then simply rescale the power spectral density for O3A, and the formula to do that is presented on the lower right, and these give us the blue curve you can see on the right. This is the estimated sensitivity. When interpreting this, we do need to keep a couple of things in mind, and that is that we can't necessarily do a very clear comparison between the results here and the results from other pipelines, either in this search or from other works. This is because, as I mentioned earlier, we have that random walk signal model that accounts for stochastic spin. So even though our H0 95% is actually larger than the Bsd results, they're not numbers that are directly comparable. They look like they're the same, but they're each constraining a different set of physics. So it's actually important that we have both these results. The best sensitivity we obtain with this particular search is for G353.6 minus 0.7, and we managed to get as low as 2.68 times 10 to the minus 25, around 172 Hertz. Next, we have the dual harmonic Viterbi algorithm. Again, we followed the same process. We set upper limits in the sample bands, shown in the plot on the right in orange crosses. We then managed to obtain sensitivity in the full band using the scaling shown on the lower right, which it's worth noticing that this now has both those F and 2F components because we're talking about dual harmonic emission. Once we do that rescaling, we get the points in blue in the panel on the upper right. Now, there are a few assumptions that go into this. On top of the standard new signal model we have to account for, where we have emission at both F star and 2F star, we have to assume specific details about the inclination and wobble angles and the polarization. And for the polarization, we actually assume that both signals are linearly polarized, which is the worst case scenario overall, but offers us the greatest improvement over a single frequency search. The best sensitivity we obtain with the dual harmonic Viterbi algorithm is 2.9 times 10 to the minus 25 for G65.7 plus 1.2, G189.1 plus 3.0, and G353.6 minus 0.7. And again, it's very hard to try and compare these to the limits set with the single harmonic Viterbi or Bsd algorithm because we have a different physical model and a different signal model encrypted into the code. So it's not really clear what those comparisons mean. Now that we've had a look at what our strain limits are, we can start to look into the limits on the underlying physics. The most obvious thing to try and constrain is the ellipticity. A standard continuous wave signal model will predict emission at 2F star coming from a varying mass quadrupole. This fits very well with the signal models used for the Bsd and single harmonic Viterbi algorithms, and we can rescale with the very standard formula that we can see on the left here. These give us results such as those shown in the upper right panel, which are the results for the Bsd algorithm. The dual harmonic Viterbi algorithm manages to constrain ellipticity from the same physical model. However, we also have to make that assumption that we have emission at both F star and 2F star, and both the components are linearly polarized. When we do that, and we're very careful about it, we can still constrain the ellipticity, and these give us the results on the lower right panel. The key thing to notice here is that for both the Bsd and dual harmonic Viterbi algorithms, we managed to get below about 10 to the minus 6, which is similar to the theoretical upper limits on ellipticity in neutron stars, which means we're starting to probe some of the more extreme variations on equations of state and how that ellipticity could have formed. The other thing we can do is we can look at R-mode constraints. Or to be more precise, we can do this with the dual harmonic, we can do this with the single harmonic Viterbi algorithm and the Bsd algorithm, but we cannot do this with the dual harmonic Viterbi algorithm. That's because that particular signal model is fundamentally incompatible with this kind of gravitational wave emission. So it is not just meaningless, but actually incorrect to try and make that comparison. For the other two, it turns out that when you have gravitational wave emission from a mass current quadrupole, you can actually rescale your gravitational wave strain that you limited using a standard search based on ellipticity. And you can turn that into a limit on the R-mode amplitudes in your rotating neutron star. If you do that using the formula on the left, you get the results on the right, where the top panel is the results from the Bsd panel, pipeline, and the lower panel is the results from the single harmonic Viterbi algorithm. Now, a key thing to notice here is that we managed to get below 10 to the minus 3 for both algorithms quite low, and below 10 to the minus 5 at higher frequencies. This is exciting because R-mode amplitudes, we have I apologize. For R-mode amplitudes, we managed to get lower than the theoretical prediction for nonlinear saturation mechanisms, which would predict about 10 to the minus 3 above 150 hertz. So we're actually getting a couple of orders of magnitude below that, which is very exciting. Again, this is letting us actually get at the underlying physics for what's generating these continuous waves. Looking at my personal timer, I think I'm running a little bit short on time, so I will not spend a lot of time on the comparison. I was just going to mention that there's a different philosophy in how this search was done. Most previous searches on the left have put a great deal of computational resources to try and look for a few targets using everything they have. Because this data was soon to go public, we decided to use efficient pipelines to try and search a broad variety of physics as quickly as possible. Despite that, we were able to improve on most results, with the notable exception of CAS-A and G347.3 minus 0.5 from the PAPA 2020 results. So just to summarize, we report no continuous gravitational wave signals in O3A data. We have the first limits on these targets that include stochastic spin wandering, and the first limits that consider dual harmonic emission. We managed to constrain both ellipticity and R-mode amplitudes below the theoretical upper limits, and our results cover a wide parameter space and are based on a series of more efficient methods. As we manage to refine these methods and improve our data collection, we'll be able to improve the probability of a future detection. If you want to see the paper behind this talk, there is a version on the archive linked at the bottom, and that should be updated hopefully soon. Thank you.
Thank you very much, Lucy. Very clear talk. Any questions, please? We have about 3 minutes for questions. Maria Alessandra, please.
Hi, Lucy. Thank you very much for a wonderful talk. I really enjoyed it. I don't know if I missed it. I think you might have said it at the beginning. My question is, why didn't the Bsd search do all the targets?
Yep, that's a good question. So when we were choosing the targets, it simply came down to balancing how long the search would take, what computational power we had available, and the relative power and cost of each search. The Bsd algorithm was the most sensitive algorithm we used in this search, but it was also the most computationally expensive. So they had to be a little bit more strategic about which targets to search. Given infinite computing resources, they probably would have done everything, but alas, that's not the world we live in.
Thank you.
We have time for another question for Lucy. Okay, well, I don't see any blue hands, and if for some reason the blue hand isn't working for you, please don't hesitate to pop a question into the chat. It's free for use. But if there are no other questions, then thank you again very much, Lucy. And the next talk will be by Bernard Muller, and he will be presenting a review of gravitational wave signatures of magnetic field generation in core collapse supernovae.
Yeah, thank you, Andrew. Let's get started. Yeah, delighted to be here virtually at the Master Grossman meeting, and thank you, Andrew, for the kind invitation to talk on this occasion. Is everyone seeing my screen?
Yes, but we can not in full page mode.
Yes, so something is not allowing me to go to full screen. Let me just a second. This has never happened before. I think it should show up in full screen now. Yeah.
Perfect.
Good. All right. So thanks again for the kind invitation to talk at the Master Grossman meeting on this very intriguing subject, which was suggested to me, the gravitational wave signatures of magnetic field generation in core collapse supernovae. I think this is an intriguing subject because actually we don't have that much on that topic yet, but there are a few things that are very promising that I think it's worth telling a broader audience. I very much understand this as this entire talk as a quick summary of what we know about the core collapse supernova gravitational wave signals so far, and the surprises that probably lurk now that we're moving towards integrating magnetic fields more and more into models of core collapse supernovae in all different phases. And just to remind people, when we're talking about core collapse supernovae and their gravitational wave signatures, it's of course one of many signatures in the entire that are a potential probe for the entire core collapse supernova problem, among many others. So among other multi-messenger signals like neutrinos, among indirect signatures like nucleosynthesis yields, and of course the observable transients and the neutron stars. And some of what I'm going to say is, of course, intimately connected to the story of transients and the story of neutron star formation, especially when it comes to the aspect of magnetic fields in core collapse supernovae, because the gravitational waves, as you'll see, in a sense, so at least as far as we know them today, may probably be just one among many signatures that give us circumstantial evidence about the kind of effect that magnetic fields may have in core collapse supernova explosions. Now, I can't delve immediately into magnetic field generation in core collapse supernovae and the associated gravitational wave signatures. I should probably start with giving a quick refresher about how we think core collapse supernova explosions work. Somewhat simplified picture because there might be other scenarios that I'm sweeping under the rug. But the basic story is you start from a massive star with the characteristic onion shell structure. You form an ion core. Once the ion core grows sufficiently massive, it becomes unstable to collapse. eventually the collapse is halted when you reach nuclear density. You form a proto-neutron star. The rebound of the core after overshooting nuclear density launches a shock wave, and that shock wave initially stalls at about 100, 150 kilometers above the neutron star surface. And to get this to turn into an explosion, you have to somehow deposit energy behind the shock to revive it. Now, there are two scenarios that are seriously considered nowadays, I would say, as occurring in a reasonable number of supernovae. The vast majority of those is probably the neutrino-driven, covered by the neutrino-driven mechanism, where the idea is that you tap the thermal energy of the neutron star, and that's radiated away by neutrinos from the neutron star core or from the neutron star surface. Part of those neutrinos are absorbed behind the shock. That heating, in conjunction with multidimensional hydrodynamic fluid flow, eventually drives the shock out. The neutrinos basically increase the thermal pressure behind the shock. Hydrodynamic fluid instabilities like convection can aid this by transporting hot stuff out towards the shock from the neutrons, from closer to the neutron star surface. They also exert effective turbulent pressure on the shock, so there's a combination of effects involved. That's the idea of the neutrino-driven scenario, which we think obtains in perhaps 99% of all explosions. In addition to convection, the convection behind the shock is driven really by the neutrino heating. You have heating from below in an accretion flow that makes conditions for convective overturn. In addition, there's another instability, so-called effective acoustic instability, that manifests itself as global oscillations of the shock surface. That's characterized by different spatial scales and different time scales. This is also known as the SASI, standing accretion shock instability. There's also multidimensional fluid flow inside the neutron star, so similar to the convection behind the shock. There's convection driven by the cooling at the surface and deleptonization at the surface inside the proto-neutron star. And to already give you a glimpse ahead, these various multidimensional fluid instabilities are, of course, what makes this phenomenon interesting as an emitter of gravitational waves. Now, aside from that, we have suspected for a long time that there are probably some supernova explosions that are driven by magnetic fields that tap the rotation of either the neutron star or an accretion disk around a newly formed black hole. The reason for that is that the neutrino-driven explosion mechanism, we believe, is inherently limited to energies of about 2 × 10⁻51 ergs and cannot explain the most energetic supernova explosions that we observed, so-called hypernovae. Now, about magnetic field generation in core collapse supernovae, I should, however, say that in this context, we're not really only talking about these very powerful magnetorotational explosions. The magnetic field amplification may alike play a role in the garden variety of core collapse supernovae. And we know, for example, that of the order of 10%, not going to be tied down to the exact number, but of the order of 10% at least of young neutron stars are born as magnetars with very strong dipole fields. The question is where that comes from. So we have grounds to believe that magnetic field amplification can be important, not only in the context of the variety of very powerful but very rare core collapse supernova explosions where the magnetic fields are really responsible for powering the explosion. Now, on to gravitational waves from core collapse supernovae. How do gravitational waves come into play? Well, gravitational waves always arise when we have, in simple terms, a change, vanishing second derivative of the mass quadrupole moment. At least that's the Newtonian approximation. Einstein's famous quadrupole formula shown here. And if you break that down just by dimensional analysis, then you'll find, well, this is going, the amplitudes, the strain that you're going to measure is going to scale with the mass involved, the radius of the system, some asymmetry parameter, and the typical frequency of the involved mass motions, if they're periodic or quasi-periodic or have some preferred frequency scale, which you get even for turbulent processes like convection. So the key thing is, if your system is sufficiently asymmetric and you have some amount of material from the order of, let's say, 10 to the minus 2 to, or a few times 10 to the minus 2 solar masses in the gain region, and several tenths of a solar mass in the protoneutron star convection zone, involved in reasonably fast non-spherical motions, you'll get gravitational wave emission. Now, I already emphasized the importance of non-radial fluid flow in the context of neutrino-driven explosions. So you can immediately see that these turnover motions or global oscillation motions of the shock will give rise to gravitational wave emission. But on top of that, there might, of course, be other processes that lead to gravitational wave emission if you add rotation as an ingredient in the gain. So you can have, and that has really been for a long time, the focus of gravitational wave research on core collapse supernovae. You can have gravitational wave emission simply if your collapsing massive star has a rotating core, then that rotating core will be slightly deformed by rotation. And during the collapse and rebound, well, you'll get a quasi-radially collapsing and then quickly re-expanding core. And it has a finite quadrupole moment to begin with. So that's going to give you a gravitational wave signal. And if you have very strong rotation, one other thing that we knew for a long time could happen was that you might be able to develop triaxial instabilities, bar mode instabilities, that could then actually lead to very powerful gravitational wave emission. The rarity of these events that involve rapid rotation have, however, in recent years, led the research a bit away from focus on those particular scenarios, even though these are very interesting in principle. And much of the research in recent years has really focused on the emission of gravitational wave from these instabilities in the neutrino-driven mechanism. And in order to see what magnetic fields might do to those, it's first important to give you a brief summary of what we learned about the gravitational wave emission from those instabilities in normal garden variety supernovae with slow or no progenitor rotation. And we have actually unearthed quite a bit on that and now understand that signal theoretically very well. Part of the reason is that there has been a great success story of successful explosion modeling in 3 dimensions in recent years. So the long dearth of explosion models in supernova theory, that's really long over. By now, several groups, our own included, the Monash MPA group included, have come up with a lot of 3D supernova explosion models. Friends in Princeton, for example, have obtained a large range of 3D explosion models as well. And those have really been an excellent basis for understanding systematically the gravitational wave emission in core collapse supernovae from this garden variety of explosions. Now, how does that, the gravitational wave emission from such a normal supernova look like? This is something that I suppose some people here may have seen already, but some may not have. So we've initially, what people thought when they post-processed the gravitational wave emission from those big hydro simulations was that well, it looked quite stochastic, but we've actually discovered in recent years that there's a very definite structure behind that apparent stochasticity from the gravitational wave emission from convection and or the standing accretion shock instability. So the spectrograms of those signals, if you do them properly, they actually show very, very definite structures. So typically what you'll always see almost invariably is you'll have a rising emission band that goes from about 200 to, well, above 1,000 hertz usually. And that has been identified as the manifestation of an F or G mode, the mode of that oscillation mode of the neutron star changes character really during the explosions. That's what you find if you do a closer analysis of the mode structure. But it's basically a buoyancy stabilized oscillation mode that you see in the gravitational wave emission, less so than the flow outside the neutron star surface that excites these modes only really. So the phenomenon that you see that makes the gravitational waves is really an excited forced oscillation, so stochastically forced oscillation mode, rather than the turbulent fluid flow behind the shock itself. Yeah, and the nice thing about that is that the oscillation mode has a very definite frequency, and you actually get quite distinct features in the spectrograms. And if you were in the very fortunate position that you could observe one of these events reasonably nearby, then that the frequency of that F or G mode would actually tell you very much about the properties of the neutron star. So some lowest order analytic analysis actually gives you quite a nice and well-fitting relation of the F-G mode frequency that you see in the gravitational waves to the neutron star parameters like the mass, radius, and surface temperature, which you could potentially directly constrain by the neutrino emission. And quite interestingly, also the overall amount of gravitational wave power that is radiated can also be attached, as we've learned, to some physical property of the entire process. Basically, that's relevant to the entire turbulent flux that impinges on the neutron star surface, integrated over time. And there's a quite direct relation between the overall gravitational energy emitted in gravitational waves, which might potentially be constrained by an actual detection, and the sort of average parameters of this F and G mode over time times the duration of the emission and the turbulent energy of the flow in the region behind the shock that forces these oscillations. Now, on top of that very universal signature of this surface G mode oscillation, you see in some cases when you have as an additional instability in the post-shock flow, these shock oscillations, you'll sometimes see an additional emission at relatively low frequencies of around 100 to 200 hertz by this corresponding to the frequency of the standing accretion shock instability that basically has a frequency that traces how your shock expands and contracts very nicely. Whether you can, of course, measure the spectrogram with such good resolution that you can actually see this in gravitational wave is another question, admittedly. And the interesting thing concerning that is, of course, that this happens in the region of frequency where the currently operating detectors, Advanced LIGO, Virgo, and CAGRA, are most sensitive, and where some of the third generation instruments like the Einstein telescope and Cosmic Explorer will also be most sensitive. All right, now, what do we expect the magnetic fields might do to this? And on top of this signal, that we now understand very well from normal core collapse supernovae, at least theoretically. Where could magnetic fields come into play and modify this? And as I indicated before, very often we discuss magnetic fields generation in core collapse supernovae only in the context of rapidly rotating progenitors, where the idea is that the differential rotation that you then find in the supernova core after collapse generates the strong fields on the fly, either by the magnetorotational instability, by some alpha omega dynamo in the neutron star. And then the result is that you get a very powerful hypernova explosion, as you see over here. But this is, I want to emphasize, by no means the only way magnetic fields could come into play in core collapse supernovae. For one reason, it's also on the table that in some massive stars, for example, after massive stars that have arisen from main sequence mergers, you might have extremely strong fossil fields that are strong enough to influence the dynamics of the supernova explosion after the collapse of the iron core. You could also potentially generate magnetic fields by these instabilities behind the shock, by the convective flow on the fly, even if you don't have rotation. And even if you don't have a rapidly rotating progenitor, you might still spin it up. For example, if you have a substantial amount of fallback onto the young neutron star, there's actually a very little amount of fallback that you need in order to spin up a neutron star quite a bit. So the prevalence of magnetic fields where they might have some effect could actually be a lot wider than just those extreme explosions in the context of which we typically discuss rotation and magnetic fields. Now let's move on to the kind of signatures that you could get if you have one of these scenarios at play. And as I emphasized on the previous slide, very often the signatures that might indicate that magnetic fields and or rotation play a role would of course be very circumstantial, would of course be somewhat ambiguous, and sometimes you don't have an immediate smoking gun for magnetic fields being generated in the core collapse supernova interior, but you could just point maybe at rotation having a significant role, or at least being present. Whether it has a significant role on the supernova explosion mechanism is then another question. But this, I think, is still worth remembering. As I said earlier, this is a scenario that has really been discussed for a long while. What happens if you have fast progenitor rotation? What kind of signatures do you get? And I think this is something which many people know very well anyway. In that case, as the first smoking gun that rapid rotation would be involved, is you get a signal from the rebound of a rotationally deformed core, which has the advantage that it has a very regular shape as the signal. So this very regular characteristic shape with about 3 spikes or so, that is very templatable and can be very well used for template-based searches to identify these things and actually measure very precisely the amount of rotation that might be involved in such a supernova explosion. So quite a few years ago, some of our colleagues already demonstrated that if you actually have rapid rotation of the core and the concomitant gravitational wave signal from the rotational bounce, you could actually very well constrain the amount of rotation in the progenitor as measured by this parameter T over W, so the ratio of rotational kinetic energy versus binding energy of the progenitor core. And that's, of course, a very important piece in the puzzle, because if you can already pinpoint for a certain supernova in our galaxy how rapidly the progenitor rotated, that will indirectly give you further constraints on what happens during the supernova if you find certain other signatures from gravitational waves on neutrinos or whatever. Now, what has intriguingly though received much less attention is the question of whether rotation and magnetic fields do something on the post-bounce emission of gravitational waves as well. A bit more has been done on the influence of rotation on that post-bounce gravitational wave signal. But we recently thought that it was also worth investigating whether magnetic fields have more of an impact on that post-bounce gravitational wave emission. So this is something that we did recently with my former honors student, Rylan Jardine, who did a parameter study of 2D models. So restricted to axis symmetry because the computational cost of 3D models is still so high that you can't scan the parameter space in initial magnetization and rotation that broadly in 3D. But this at least gives us a bit of a hint of where we can explore interesting effects in 3D. And what Rylan really found is that by themselves, the magnetic fields, it's actually very hard for the magnetic fields to significantly impact the gravitational wave emission, even if they become somewhat important in aiding the development of an explosion, as in this model here, where contrasted with the same simulation with a very small initial or a smaller initial magnetic field, the magnetic fields actually help you revive the shock about 200 milliseconds after bounce. Even in that case, there's really very little characteristic differences in the spectrograms and the amplitudes of the gravitational waves that you see. There are some indirect effects. So you'd see, for example, that this low frequency emission that you have in the weak field model, that low frequency emission transitions into a declining trend in frequency in the strongly magnetized model, but that's really just an indirect effect because of the fact that the magnetic fields actually help shock expansion in this case. And for that reason, the frequency of this of the shock oscillations really goes down with time. And only in the case where you
Bernard, if I can interrupt, I apologize.
Yes.
Just you've got 2 minutes. Thank
yes, I'll speed up and we'll quickly finish. And only in the case where you have rotation and rapid rotation and magnetic fields combined do you really see a major impact on the spectrum and on the gravitational wave emission. And there's hints that there might be some very interesting phenomena in there. So something which is very important for the gravitational wave detector people to take into account, what we find in strongly magnetized and rapidly rotating models is that the typical relation that we have for the characteristic neutron star F oscillation mode that you see, that seems to be broken completely in the case of rapid rotation and strong magnetic fields. And some interesting phenomenon that actually occurs, and I have to confess, we don't really have a good explanation for what's going on there, is that we do see very strong late emission after the onset of the explosion, which is spread across a wide range in frequencies, so up to high frequencies. So there might be some interesting phenomenon there. The big downside is, of course, that this doesn't help your detectability a lot because the extra strong emission that we see in very strongly magnetized models is just not in the right frequency bands. I'll skip this slide here and go to something to finally wrap up, which leads to the one thing that this talk was really asking for, namely direct hints or direct signatures of magnetic field amplification in core collapse supernovae. Now, is there anything on that head? Well, there might be direct signatures of magnetic field amplification. So I want to point you to a very nice recent paper by our colleagues in France and Spain, who actually did a slightly different approach and did very long time anelastic simulations of proton-neutron star convection, where they could follow the development of an alpha omega dynamo over seconds really. And something that they find is that in the case of rapidly rotating neutron stars, they get very strong gravitational wave emission towards late time, so much stronger than for the case of slow rotation up here. And the interesting phenomena that you see is once the strong field dynamo really reaches saturation, you get very characteristic low frequency excess emission and also very strong low frequency emission here. So this is basically the smoking gun that we could be looking for. So relatively sustained long gravitational wave emission over the first seconds after the collapse, which then eventually leads to a establishment of a very strong low frequency plateau and a shift of the preferred gravitational wave emission frequency as a sign for a dynamo kicking in. So these guys have also come up with something of a physical explanation of the kinds of modes that might be responsible for that. But in the interest of time, I think I have to wind up here and leave up my conclusions and be happy to take questions.
Thank you very much, Bernard. Well, those are really interesting results. We have time for maybe 2 minutes for questions for Bernard. Do I see any blue hands? While we wait, Bernard, just a quick one from me. You mentioned the fallback, which can of course spin up the neutron star a lot. Is there a specific prediction there in terms of magnetic fields? Are you suggesting that, for example, there'll be enhanced generation of magnetic fields potentially?
Yeah, that's actually a very, very good but also very difficult question, Andrew, because so what we can actually say is we and now a few others have done simulations of the amount of spin up that you can get by fallback. And the result is basically that you easily get as much angular momentum as you need to spin up your neutron star to a few milliseconds, 3 milliseconds, say. But no one has really taken the second step and said, so how does that actually lead to field amplification later on? And as you know, there are also a lot of other questions involved to answer that, because by that time, I mean, the question whether that fallback stuff is really accreted or whether it interacts with the magnetosphere of the newly born protoneutron star and maybe is channeled around and you extract the energy in some other form before depositing the angular momentum onto the neutron star. That's quite a difficult question. So I think this is something that's where I can just invite people to do further investigations.
No, very interesting. Thank you very much, Bernard. Okay, we are actually out of time on that one, so I would invite people who have further questions for Bernard to put them in the chat box, and I'm sure we'll be happy to answer them. The next speaker is Odis Halim, and he will be speaking about multi-messenger analysis of core collapse supernovae. Please share your screen, Odis, and you have 15 minutes before questions. Thank you.
Yeah, thank you, Andrew. By the way, can you see my screen in one page, let's say, the first page?
I can actually see it in 2 pages. There's slide 1, okay, and then slide 2 is next to it.
1 second. Okay, this one, I guess.
Perfect, thank you.
Okay. So yes, good morning, everyone. I'm Odis Halim, and here I would like to present our work on the joint analysis method on gravitational waves and low energy neutrinos to detect core collapse supernova. And this work is basically in collaboration together with Claudio Casentini, Marco Drago, Viviana Favone, Kate Schulberg, Carlo Figurito, as well as Giulia Pagliaroli. So first of all, I will show you the layout of this work, which is the first one is the goal and the scheme of what we have done so far. And then we move on to the messengers and waveform models that we have been using. Then we move to the data and analysis. There will be several different sections on this. And we will show you the results step by step as well. And in the end, I will sorry. in the end, I will conclude everything. So as we know that in 1987, there has been one core collapse supernova event nearby our galaxy in Lakshmana Cloud, 50 kiloparsec, that has been detected in multi-messenger way, which is from electromagnetic as well as neutrinos here in the very left figure. And this object is basically comes from massive stellar progenitors that have masses of the order of 8 solar mass or above that undergo their life cycle, let's say, and in the end it ended up as being core collapse supernova. And the idea is that not only that it produces electromagnetic waves as well as neutrinos, but it is also assumed to produce gravitational waves. Therefore, with that in mind, we try to combine especially these two messengers, the gravitational waves and low energy neutrinos, in a together strategy for this kind of object search. So as you can see in this chart, the blue lines here are the analysis, let's say, strategy for gravitational waves, in which data from LIGO Virgo is analyzed by CWB analysis pipeline, which is the general pipeline for this kind of search. I will explain you later about this. And then from this analysis, there will be list of GW gravitational wave triggers. And then on the other hand, there is also the red line here, red charts, in which it is basically the explanation of the analysis of low energy neutrino data from low energy neutrino detectors with the analysis of something called 2-parameter method. This is basically our new proposed idea for this analysis, which is the modification of the standard method. And from this, there will be coincidence analysis among different neutrino detectors that produce a list of triggers, neutrino triggers, in which these triggers will be, again, subject to coincidence analysis together with list of gravitational waves trigger in order to find the multi-messenger signals. And by the way, this work that has been done up to now, we put already in archive and it's online just this morning, basically. So the messengers that we use, first of all, is gravitational waves. And we pick two different classes, basically. The neutrino radiation hydrodynamics, and in this case, we choose Radis model with a given mass as well as given amplitude of gravitational wave data, let's say. And then the other class is that it's called rapid rotation and magnetic field from Dimmelmeier and Seidegger model with a given detail in the table number 1 here. And the difference between these two classes, of course, we can see by plotting the amplitude evolution. So in this case, for Radis model, we plot here, and the amplitude is of the order of 10 centimeters. And the period of this kind of signal is of the order of less than 1 second. Meanwhile, for Dimmelmeier here, in this case, the amplitude is of the order of 600 centimeter, which is 1 order of magnitude higher, basically. And the period is of the order of 0.1 second, less than 0.1 second. And in that case, based on these several models, basically, we plot the efficiency curve as a function of distance for the models that we use. And of course, we can see that for Radis model, they are all in lower efficiency curve because, of course, the amplitude is lower comparing to the other models. And so let's move on to the low energy neutrino model that we use. In this case, we use 2 different models, which is called Pagliaroli as Supernova 1987A semi-analytical model, and the other one is Hudefol numerical model with different mass progenitor. And here in the table number 2, there are also the expected number of neutrino events that should be detected by different detectors for different energy threshold. And then on the figure on the left is the luminosity of neutrino for different flavors, especially the dashed black line, which is say S11.2, which is our model basically. And it is also plotted the average energy for the Hudepol model. And moreover, in the figure on the center, it is the curve for Pagliaroli supernova 1987A. And it is basically expected that the background is somewhat flat Poissonian with some fluctuation, of course. And then the injection follows somehow the double exponential model, which raised very steeply in the beginning and then decaying slowly exponentially. And then on the figure on the very right is the efficiency curve as a function of distance, of course, for different supernova model and for different detectors in this case. And of course, for example, here the green lines are from Super Kamiokande detectors for two different models that have higher efficiency among all the others. And so in the data analysis itself, for gravitational waves, we use CWB pipeline, which is called coherent wave burst basically. And it is burst unmodeled search, and we don't have to have any templates, and we search for coherent excess energy among different detectors by using maximum likelihood. And in fact, the first GW event is detected online by this pipeline actually. And this uses time frequency analysis with Wilson-Daubessius Mayer wavelet. And here on the figure, it shows the very first gravitational waves event detected by this pipeline in terms of time and frequency map, basically. And then let's move on to the low energy neutrino analysis for the standard method. So basically the idea is that suppose we have a detector, let's say in this case LVD, and then we count the events that are recorded by this detector, and if they are above a given threshold. In this case, in the figure here is basically the horizontal red line is the threshold, the y-axis is the energy, and the x-axis is time. So we will have time series of events with a given energy, basically. And in order to give significance of different events, the idea is that we open the binning of the order of 20 seconds, sliding in time 10 seconds. So in this bin, let's say, we count the number of events inside. And in this case, it is really difficult it is not possible to say which one are injections, which ones are due to background. And so the idea is that we simply count the number of events inside this bin. And then this number of events is called multiplicity. And this multiplicity is basically the basis in order to calculate the significance. Here it is defined the imitation frequency, or FIM, or we can also say false alarm rate as a function of multiplicity, of course, based on Poisson distribution, with the assumption that the background frequency of the detector is somewhat following Poisson Poisson distribution, and it's written in this way. And moreover, this is the standard way. And anyway, from this, we basically try to introduce another parameter that may be important in this analysis. So our proposed method is basically we put a new parameter called C, which is the multiplicity divided by the duration of the binning here. Let's call this bin as a cluster. So the duration of the cluster. And so the duration itself is basically the time difference between the last event and the first event. And the idea of this is that if it is due to real signal or injections, let's say, the events will be confined in a shorter duration. As you can see here in this figure, basically there is higher density of events in the beginning of the time. So basically, we assume if it is due to real signal, the Xi will be higher comparing with if it is due to background. So the false alarm rate that has previously written in this way, basically, we change the probability to be depending on two parameters, not Poisson anymore, let's say, but K, C. And after some calculation, we put this kind of term here, and the detail can be seen in this literature. And so we put also the simulated background and simulated background plus injections. As you can see in the figure on the top right, is basically that if this kind of clusters are due to background, they all have C value in a lower region. But if it has stronger injections, like 65 kiloparsec in this case, they all have in the higher C values. That's the idea of the two-parameter method, actually. And then in the multi-messenger method, the strategy is simply we combine via coincidence analysis, of course. And then the threshold, first of all, for single detector neutrino is 1/100 year, following Snr's threshold, basically. And then for coincidence analysis, we put the threshold of 5 sigma. And in this case, the joint false alarm rate can be written in as a multiplication of false alarm rate of from each detector, as well as similarly for total multi-messenger analysis. And the false alarm probability simply follows Poisson distribution, of course. And so here,
you have 2 minutes, please.
Here is the result of one detector neutrino. So for supernova 1987A signal at 60 kiloparsec, in this case, in this figure, we have the C versus multiplicity plot, and the red line here is basically the multiplicity given for 1/100 year, in a sense that for multiplicity above 8, for the standard method, they are all recovered. The injections are all recovered. But with the two-parameter method, we will have new additional recovered injections in the red area here, with even though the multiplicity is lower, but the C is as long as they are high. So the efficiency is from 73% with the standard method to 83%. And then we do similarly for coincidence analysis between gamelan and LPD. Here is the efficiency curve, and the efficiency can be written in this way for 50 and 60 kiloparsec. And then we did also for multi-messenger. First of all, we tried gamelan plus gravitational waves, as well as gamelan plus LPD plus gravitational waves. Here is the false alarm rate, the new method, the two-parameter method versus the one-parameter method. And the efficiency can be seen in these two different blocks, like from 73 to 83% and so on. And the total efficiency here needs to remember is that the gravitational waves recovered by CWB, for example, here is only 33%. But with a combination of multi-messenger, we managed to have 33.1% of 5 sigma triggers. Meanwhile, here 33% is that they are all very poor in terms of significance. With the triple analysis, we can have higher significance with a better efficiency. And if we put two-parameter method instead, the efficiency will be somewhat higher a little bit in this case. And we move also for different signal model, in this case Hudefeld, and it shows from efficiency 30% to 33%. And in this case, we need to remember that they are all 5 sigma. And moreover, for gravitational wave from CWB, they are all in a very bad significance in this case. And yeah, that's it for our work up to now. Here are the conclusion. And thank you very much.
Thank you very much, Adis. That's great. Questions, please, from the audience. Well, we have 3 or 4 minutes for questions. While we wait, Adis, can you sorry, I'm not an expert in this at all, but with the low energy neutrino data, how should we interpret that? For example, that data presumably has different priors to the gravitational wave data if we were looking at it in that Bayesian way. Are we confident that we can do a joint analysis? What maybe the better way to say it is, are there any dangers in doing a joint analysis?
Of course, there are some dangers somehow in a sense that for when doing this, of course, we put the lower false alarm rate threshold for gravitational waves analysis with CWB pipeline. And that's why what we recovered is here, as I said before, has very low significance. And this, the challenge could be that it could be in, let's say, in real analysis without injections, in a sense that we may recover that those events in gravitational waves are not really low threshold, are not really weak events, in a sense that they may be noise instead of real events, because we lower the threshold. However, taking into account that we do the coincidence analysis between gravitational wave and neutrinos, we suppress much more this background from the gravitational waves itself. So in this case, there is this challenge, but we may be able somehow to tackle by doing this coincidence analysis. So with triple. Is that answering? Mm-hmm.
Yeah, very clear. Thank you very much. Yep.
Thank you.
Okay. Any final short questions? No? Okay, well, thank you very much again, Odis, for your talk. The next speaker is Dr. Irene de Palma, and she will be speaking about deep learning for core collapse supernova detection. Thanks, Irene.
I'm sharing the slide. I hope you can hear me and you can see the slides.
Yes, perfect.
Okay, so today I will present this latest work that we have done with this group of people, Pablo Cerda Duran, Marco Drago, Melissa Lopez and Fulvio Ricci, about the detection of core collapse supernovae using the deep learning algorithm. So to move on, we heard that, sorry for that. So the detection of gravitational waves from core collapse supernova explosions is a challenging task, as we heard. And so is it key to connect between multiple messengers, including neutrinos and electromagnetic signals? So in this work, we present a method for detecting this kind of signal based on machine learning technique. And the impossibility of using template matching technique in this case due to the big complexity and stochasticity of the waveform makes it necessary to find new ways to improve the detection statistics. So we already proposed the use of machine learning technique to take advantage of these peculiarities of the core collapse supernova gravitational wave signal. And in particular, we focus on the monotonic rays of the gravitational wave signal in the time frequency plane due to the G modes excitation, which is a dominant feature present in the gravitational wave spectrum. So to implement our search method, we have pursued an approach similar to the previous work. So we consider a parametric phenomenological waveform that is designed to match the most common features observed in numerical models of core collapse supernovae. And we focus our attention on G modes excitation, that is the common feature of all models developed that is responsible for the bulk of the gravitational wave signal in the post-Planck's evolution of the broader neutron star. And so the aim of the phenomenological template is to mimic the rising arch observed in the core collapse simulations. And for this purpose, we consider damped harmonic oscillator with a random forcing in which the frequency varies with time. The phenomenological templates used in this work differ from the previous one in two aspects. The first one is that we use a new and more flexible parameterization for the frequency evolution. And the second one is that we use distance as a parameter. And so these phenomenological templates are calibrated to mimic the features in the numerical simulation for non-rotating stars. So on the left of this slide, you can see an example of the phenomenological waveform. And the upper panel shows the strain as function of time, and the lower one, the corresponding spectrogram, so frequency over time. The white dotted curve shows the time frequency dependency used to generate the waveform, and the white circles represent the pairs, time and frequency used to generate the same curve. On the right, you have the parameter space of the phenomenological templates. For the development of this deep learning algorithm, including the model definition, the training, and the validation phase, we use the Keras framework based on the TensorFlow backend. So the problem is treated as a multi-class classification problem with two classes, the event class and the noise class, by using a binary cross entropy. Therefore, the output of the network is a probability vector, theta, which contains the probabilities of the template belonging to one class or another. And the classification task is then performed according to a predefined threshold that we call theta star, so that the template will be classified as event class only if this probability overcomes this threshold theta star. So to assess the robustness of our methods, we selected data from the second observing run of the advanced gravitational wave detectors. In particular, we choose a stretch of data containing glitches, so real detector data, taken during August 2017 when Virgo joined the run. And we consider about 15 days of coincident times over the three detectors, and we use this data to generate a data stretch of 2 years of time shifted data to train and test the neural network. So we have three different sets. The training set for core collapse supernova signal has been constructed, injected phenomenological waveforms of fixed distances. And for each distance, we injected 70,000 waveforms with random sky localization. 75% of the set is used in the actual training, while the remaining, so the 25%, is used for validation. And the upper distance has been chosen accordingly to the requested minimal SNR of the injected signal, in which the trace of the core collapse supernova signal is distinguishable from the noise in the image passed through the neural network. Moving on, the blind set is used to quantify the detection efficiency and to test the network. It is not involved in the training or validation procedure, but just in the test. is composed of 260,000 simulated signals with distances chosen in a uniform distribution between 2 and 50 kiloparsec with random sky position. And the blind set is bigger than the training set to maintain enough statistic for all the distances. Then the last set, what we call the test set, contains injections using core-collapse supernova waveforms from numerical simulations found in the literature. In particular, we focus on 3D simulations of non-rotating progenitors representative of the neutrino-driven mechanism. So in this selection, we include models with a variety of mass progenitors and feature in the gravitational waves spectrum. So we train the network using curricular learning, where we start training with the easiest data sets, and then gradually the task difficulty is increased. We measure the performance of the neural networks in terms of efficiency, eta CNN, and the false alarm rate, which are equivalent to the true positive rate and the false discovery rate. To improve the performance, it is necessary to minimize the false alarm rate while maximize the efficiency. So we implemented something that is called weighted binary cross entropy to penalize the classification in the algorithm. So what we do is we assign a weight to the class. So weight equal W equal 2 correspond to correctly classified the noise as well as the event class. Instead, when we use W equal 2, we meant that is it 2 times more important to correctly classify the noise class rather than the event class. So the algorithm returns the probability theta that a certain temperament belongs to the event class. We define a decision threshold of theta star of 65%. When a given probability exceeds this value, we will classify it as an event, otherwise it is classified as noise. The plot that you see on this slide shows the efficiency in solid lines and the false alarm rate in dashed lines as function of SNR computed during the validation process with the 2 different weights, and as well as a comparison with the previous work, that is the almost flat dashed line that you see in red over the 90% efficiency and about 3% of false alarm rate. In this slide, instead, we show the result of the validation process on the training set that contains the phenomenological waveforms injected in real noise in the interval SNR between 1 and 232. And so these results are shown when fixing the theta star, that is the threshold, and the weight, so the W equal 2. The results obtained when we use the network trained and optimized on the data of the blind set and test set are our final results. So the network has not been trained by any of the images of these 2 sets, so they can be used for the final test of the performance of the network. So the signals injected in the blind set correspond to the waveforms generated by the same procedure used to generate the training set, while the injections in the test set correspond to the realistic 3D core collapse supernova waveforms. So in the plot that you see on the slide, we report the histogram of the injections in the real noise. This plot shows the robustness of the decision threshold, that is the vertical red line that you see, theta star 65%, even in the case of real noise. moving on with the result, excuse me, here you see the efficiency as a function of the distance. And as you can see, again, we use the blind set and the test set to give the final result of the analysis. So at short distances, there is a difference in efficiency between blind set and test set of about 10%. But even but when we increase the distance, they seem to reach a lower limit of efficiency that is order of 60%. The final plot I want to show is the efficiency as function of SNR. So for lower for low SNR, the difference efficiency in the two cases, the blind set and the test set, is around 10% again, while for the SNR that is higher than 15, we obtain the same efficiency. So these final results assess the robustness of this method to detect core collapse supernova signal embedded in real detector noise. To conclude, we have seen that with this algorithm, we were able to identify signals from both our phenomenological template bank and for actual numerical 3D simulation of core collapse supernova. And for a signal to noise ratio higher than 15, the detection efficiency is about 70%, a default alarm rate lower than 5%, while the event distance reaches values up to 14 kiloparsec with the efficiency of 60%. So thank you very much for your attention. I will take any questions.
Thank you very much, Dr. De Palma. Questions? Yes, we have one from Gustav Chandra, please.
Hi, Irene. I have a question. So the SNR that you are mentioning is the single detector SNR, or is it the network SNR?
Is the network SNR. Yeah, sorry, I didn't specify that. So when you see SNR is network SNR, and we consider during O2, there were 3 detectors involved, so the 2 advanced LIGO detectors and the Virgo one. So when you see, for example, 15 in SNR is the network SNR, that means about 3 point something for each detector.
Okay. And for the false alarm rate calculation, it's not really the statistical significance of the event as it is done in LIGO detections, right? Means it's not giving a significance in terms of number of years or so in time.
Yeah, correct. That's this false alarm rate is computed as the misclassified noise over all classified events, and is also in deep learning algorithm. Yeah, that's correct.
Okay, thanks.
You're welcome.
Thank you very much. The next question is from Meg Millhouse.
Yeah, thank you. So on the very last plot you showed, so it's the last slide before your conclusion slide, for the test set, the efficiency starts to drop at the end. Is that just like a small number statistics thing, or is there for this particular type of search, is there a reason why for very high SNR you'd expect a drop in efficiency?
That's a really good question. We actually didn't expect it, and we don't know what causes that. I suppose it's due to the fact that in that test set we use all kind of 3D simulation of non-rotating progenitors that includes really a huge variety of mass progenitors and features. So my 2 cents on that is that this drop in efficiency is due to the huge variety of things that we are tested, while in the phenomenological templates we have just few features due to the raising arch of the waveform.
Okay, thank you. I have one more question kind of related to. Is it okay if I ask that, or does someone else have their hand up?
No, go ahead, please.
Yeah, sorry, just on this plot again too. So I might not be reading axes wrong. I believe he said that the efficiency was started around 10%, but it looks like here for SNR1, you're still getting efficiencies for the blind set of like 70%. Is that, am I misreading it, or are you getting really high efficiencies even for very quiet signals?
No. Yeah, sorry. What I said about the 10% is the discrepancy between the two sets, not the fact that we have an efficiency around 10%. So the efficiency is quite good even with SNR that is really low. And remember that is the network and SNR. But we do see in the left part of the plot again discrepancy between the blind set and the test set, as you notice for the upper right part, is about 10%, and that's probably depends on the fact that with these low values of network SNR, the algorithm cannot assess what is a real feature and what is noise.
Great, thank you.
You're welcome.
Thank you very much. Are there any other questions? I have a very quick one, ICRANet, just about do we understand what features in the signal push the classifier in one direction or another?
So if I have to choose, so this is a really important feature, I think, due to the G modes. Another important feature that we are trying to investigate is the SASI, that in this time frequency plot will appear over here. That is like a blob, and it's showing you how the proto-neutron stars moves after the collapse. And this is a really important feature in my opinion, because if we manage to track that down, and so to detect that particular feature, we cannot have the frequency of the rotation and the mass of the progenitor, but also the radius in some combination. So in terms of parameter estimation, that would be really, really important to detect as well.
Okay, great. Thank you very much. That's very clear. Wonderful. All right. Well, we're at the end of the block. So thank you again, Dr. De Palma. The next speaker is Professor Mayuri Seclariadu, and she will be talking about hunting for the stochastic gravitational wave background.
Thank you. Thank you very much, Andrew. Can you see my screen?
I think not right now, but yes, perfect.
So I don't know whether I should open the video as well or not. You tell me.
As you please. If you would like to try it with the video on, and then I'll let you know if it's breaking up.
Does it work? I believe it should work. Okay, so thank you very much. Thanks for the invitation to give this talk. So we'll talk about the stochastic gravitational wave background, implications for astrophysics, high energy physics, and theories of gravity. So apart from the detected burst of gravitational waves, which come from nearby loud sources, we expect that should exist a background of gravitational waves, which is made from all sources from the universe. Now, this should have been produced by the superposition of many sources which are weak, independent, and with our interferometers, we cannot resolve them. They may be of an astrophysical origin or a cosmological one. Astrophysical may be binary, supernovae, neutron star, cosmological inflation, cosmic strings, cosmological phase transitions. Now, depending on the strain and the frequency, you use different kinds of experiment in order to detect them. So today, I will talk about ground-based interferometers. Now, the stochastic gravitational background has not been detected so far, but we expect that soon, even probably during the fourth observing run of the LIGO-Virgo-Kagra collaboration, it could be detected as our interferometers are reaching their design sensitivity. Now, if you have just one single gravitational wave detector, and you're going to write the signal S of this detector I in Fourier space as a function of the frequency, it will have two parts, the strain H and the noise. For a stochastic gravitational wave background, the noise is much bigger than the strain. So the only way that one could be able to detect the stochastic background is by correlating the outputs of two detectors I and J. So what we do, if we assume that the stochastic background is isotropic, Gaussian, stationary, and unpolarized, we're going to build this estimator Cij, which is given in this expression that you see here in the top. I believe you can see my mouse. S, I, and J are the strains from the I and J detectors. Gamma Ij is the normalized overlap reduction function between your detectors. S0 is the spectral shape for a stochastic background that is flat in the energy density. This is a normalization. And by capital T, I denote the duration over which the Fourier transform is taken. Usually, the energy density of gravitational waves is given in a logarithmic interval of frequency and normalized with the critical energy density. This is the dimensionless parameter omega GW, like all dimensionless parameters that we use in cosmology. The frequency dependence is a power law with a value alpha that depends on what is the source of the stochastic background. So if now I go to assume that the gravitational wave signal and the intrinsic noise are uncorrelated, and in addition that the noise for every frequency beam we consider is independent, then the C hat is the omega GW plus a contribution from the correlated noise. If there is no correlated noise, then the estimator that we have built is indeed an estimator for the omega GW. But what if there is a correlated noise? And the example is the Schumann resonances, which are the global extremely low frequency peaks in the electromagnetic field of the Earth. Then in this way, the C hat will have a contribution from this magnetic noise contamination. This is a study that we did like a year and a half ago. And what we had proposed is a novel approach, which is complementary to the magnetic noise budget. There we model the background from the local magnetic field. Then we know that this via the transfer function is going to give a noise in your detector, and then the contribution that you have in this estimator C hat, it is given here in terms of the coupling functions K, I, and J, or kappa alpha, kappa I, kappa J, if you wish, which depends on your detectors, and these exponents, which as well depend on your detector. So in the plot here, we saw the power spectral density of the magnetometer data near Cassina, where is the location of Virgo, and you can easily identify the 5 harmonics here, okay? Now, this is a method that we have proposed, and as I will show in a minute, has been used in the analyzing of the O3 data of the LIGO-Virgo-Kagra collaboration. So what we have done in this third observing run, we used the detector network with the 2 LIGO twin detectors and the Virgo detector. We have the observed strain from which we can build the cross correlation, and then by an optimal combination, we get the estimator C. The advantages by using the detector network in these stochastic searches is twofold. On the one hand, this can improve the high frequency sensitivity, and on the other hand, it can distinguish between different polarizations. Now, this was the first time that the 3 baselines were combined, and the data show consistency with uncorrelated Gaussian noise. More explicitly, if we fit our models to the O3 data, we found by studying the bias factors that the Gaussian noise is preferred over both correlated magnetic noise and correlated magnetic noise with a power law stochastic background. Now, there are 2 parameters that one has to fit in these power law backgrounds, the omega ref and the alpha, which will determine which depends on what is the source of the stochastic background. Is a compact binary coalescence, that it is 2/3, is a more cosmological origin, like inflation of cosmic strings, then it is 0. And you can see here the constraints, the better constraints that we have by adding the O3 data. So here you can see the constraints on the last paper of the LIGO-Virgo-Kaggle collaboration analyzing the stochastic background. Now, if I consider that the stochastic background is made out of compact binary coalescence, then if you go to write down the quadruple formula that you have here on the right, so here the frequency is denoted by nu. If you go to take the integral over all frequencies, then immediately you see that the frequency dependence of omega, it is 2/3. So in these two plots here, on the left-hand side, it is the 90% credible band for the BNS and BBH. For the BNS, there is an uncertainty band due to the statistical uncertainties of the BNS merger rate. For the case of the BBH, in addition, we have uncertainties in the binary mass distribution. Unfortunately, at the time, there was not an ambiguous detection of a neutron star black hole system, and therefore we have put only upper limit. As you know now, from a few days ago, there are two BNS and BH and S systems. On the right-hand side, we compare the combined BBH and BNS energy spectra, and as well the 2 sigma power law integrated curves, which is nothing else than the sensitivity of your detector, for O2, O3, and as well the projections for the 2 LIGO and Virgo detectors. So more precisely, if you take a power law stochastic gravitational wave background, which you find to be tangent in one of the power law integrated curves, that means that is detectable at the 2 sigma level. There has not been detection, so the upper limit at 25 Hertz for compact binary coalescence leading to a stochastic background is 3.4 times 10 to the minus 9. So I said at the beginning that the stochastic background can give us information about the compact binary coalescence. Let me explain why I'm saying that. Here on the top, I'm writing the omega is W from CBCs. So as you can see, it depends on the energy rate at the frequency of the source. And then there is this quantity, capital R, which is the merger rate. The more mergers you have, the more omega GW you are going to get. In the denominator, this function E captures all the cosmology that you have in mind. So here we take the lambda CDI model. So the most important quantities, which are this parameter theta that you can see, which describe the binary black holes, are the masses and the spins. So what we have done a few years back, we have considered something like 10,000 different astrophysical models, and we have explored what will be the omega GW. What we have found is that even though the spins do not play a particular role, the masses are very important. In other words, as you can see, the omega GW can vary by almost 2 orders of magnitude, which means that the day that I have detected a stochastic background, that I know that is a real one and not contaminated by magnetic resonance, the day that I know that comes from CBCs, I can put constraints on the astrophysical model of black holes. Now, we can, as I said at the beginning, that was my title, put constraints on beyond the standard model particle physics. And I'm going to give 2 examples, cosmic strings and first order phase transitions. So the universe expands, the temperature drops, it undergoes a series of phase transitions which are accompanied by spontaneous symmetry breaking that can leave behind topological defects as relics of a previous, more symmetric phase of the universe. You study the homotopy group of the false vacuum to see whether a defect is formed and what is the type of this defect. And many years back, actually, with some colleagues, we have shown that in the context of grand unified theories, you have a U1 that breaks, so cosmic strings appear. Now, these objects oscillate and they emit gravitational waves. As they oscillate as well, they can, as they move, they can meet another string. They are going to exchange partners, and this position, you have a discontinuity, we call it a kink. Kinks propagate along the string, they can collide, and in addition, there are points on the string where instantaneously they move at the speed of light. We call them cusps. Kinks, cusps, and kink-kink collisions are the domains along the strings from where you have a lot of gravitational waves. Now, if you go to write what will be the omega GW, then you need to know, in this case, what is the loop distribution. In other words, how many loops I have of a given size, which is the average numbers of cusps and kinks in my network. These are given by rather complicated numerical simulations. Here you can have the snapshot of a simulation we give more than 15 years back. And now once I have fixed my model, okay, and here you can see we consider two models that are given from simulations, and the third model, which more or less we cooked it up. It's a more agnostic model that interpolates between the two. The only free parameter now that I have is the string tension, which will tell me when the strings were formed, how heavy they were, at which temperature of the universe of the phase transition these objects have been formed. So now you can see for the different models, and depending on how many kinks or cusps I will have a different omega GW. If you wish, is the corresponding to what I saw before for the different masses of the black holes. So here I show you the results that we have analyzing the O3 data. And for 3 out of the 4 cases, the stochastic analysis gives the strongest constraints which exist in the literature about the tension of the strings, which is the only free parameter I have. And this is an energy scale which cannot be reached by any accelerator like the LHC. Now, another example is first order phase transition. So the universe, as I said, expands, the temperature drops below a critical density, and that means that it's going to make a transition from a metastable phase, which I call it false vacuum, FV, as you can see in this figure, to a stable one, true vacuum, through a sequence of bubble nucleation, growth, and merger. Now, during this process, you have the formation, the creation of gravitational waves, either from sound waves or from bubble collisions or from magnetohydrodynamical turbulence. The stochastic background that you get like that, it is characterized now by a broken power law with a peak frequency, which is determined mainly by the temperature of the phase transition. And if it happens that the temperature is between 10 to the 7 and 10 to the 9 GeV, then it is within the band of the LIGO Virgo. And this is a temperature that cannot be reached, this scale, within LHC. So here in these two plots that you can see the slide, I show the stochastic background, which is produced by either sound waves or bubble collisions in the context of first order phase transition, depending on the 2 free parameters that will come from the particle physics models you have at hand, which is the strength of the phase transition and the inverse duration of the phase transition. So by analyzing the O3 data with several colleagues, we have looked for signature of phase transition within the O3 data. At first, we considered a broken power law, but in addition of the first order phase transition, we had a component that comes from CBC, because you might tell me first order phase transition might not exist, but we know that compact binaries exist, and we were able to put a limit both in the contribution of compact binaries and of a first order phase transition with a broken power law in the stochastic background. Then we took a phenomenological model. So now we're going to have a bunch of parameters, which depends on what is the particle physics model we have at hand. And there we can write the energy density of gravitational waves from a collision of the bubbles or from sound waves. And again, we're able to put constraints. So now we can go back to our friends in particle physics and say you have to tune the parameters of your model so you are within the constraints of the stochastic background that we have from the O3 analysis. Now, of course, now you may ask me, okay, you tell us about a contribution from CBCs, of cosmic strings, of a broken power law. If tomorrow I have a detection of a stochastic background, can I be able to say what is the origin? So again, with some colleagues, Katerina Martinovic, Pat Myers, what I think is among the participants now, and Nelson Christensen, we study that. So the analysis is pretty simple. So here you can see the log likelihood for a single detector pair. You can very easily generalize that for the pairs of the detectors, the 3 detectors we have. And then in order to see whether we can make a model selection, we are going to compare our models using a Bayes factor. So if you remain within the current generation of detectors, in other words, LIGO Virgo, and you go even above, like meaning of force sensitivity with 1 year of running time, the answer is that unfortunately we'll be unable to separate astrophysical from cosmological sources. If we go to the 3rd generation of detectors and we assume 2 cosmic explorers at the position of the LIGO twin interferometers today, and to an Einstein telescope at the Virgo site for 1 year of running time, then we will be able to make the kind of separation between astrophysical and cosmological sources, but attention, that will be done provided we'll be able to subtract the loud astrophysical foreground. And this is not a trivial task, but in principle, this is doable. Now, I said as well that I can, the stochastic background can tell us something about early universe. As you know, during the radiation era, there is a matter-antimatter asymmetry, which is produced. And that, if you go back to the Sakharov criteria, one of the Sakharov criteria tells you that you need a source of parity violation, which implies that in the early universe, you need a way to create a parity violation. On the other hand, you know that astrophysical sources are pretty unlikely to give a kind of a circular polarization. So if I am able to detect a parity violation, I will be able to distinguish between astrophysical and cosmological background, while by studying, analyzing the polarization of the stochastic background, I can put constraints on parity violating symmetries. Now, some studies have been done in the past about Chen-Simon's gravity, about axion inflation, and very recently, a few months ago, we studied turbulence in the primordial plasma. So what you do if you want to take the circular polarization, now you take the two-point correlator, which is going to be given by the Stokes parameter I and V. V captures the polarization of the stochastic background. If you have no polarization, the V will be equal to 0. So here is the cross-correlator estimator, which just generalized the cross-correlator estimator for the case of an unpolarized stochastic background. But now this dimensional parameter, which gives you the energy density of gravitational waves, this omega GW, is going to have a contribution from the polarization degree, capital pi. This gamma V and gamma I are the corresponding overlap reduction function for the detectors D1 and D2, okay, for the Stokes parameters I and V. And this polarization degree is either 0 if you have fully unpolarized background, or plus minus 1, depending if you have fully left or right polarization. So what we have done, again, we took the O3 data and we searched for parity violation with a uniform power in pi. And what we have found is that there is no evidence in the O3 data about parity violation. We could put a constraint on the amplitude of the omega GW, but we could not give a value. We cannot estimate the degree of the polarization, neither the value of the exponent in this for the frequency, for the power law dependence of the omega GW. Then we said, okay, let us be less agnostic. Let us do a kind of model-dependent search. So there is a proposal in the literature about helical turbulence in the early universe as a source of the parity violation, and this has been studied with magnetohydrodynamical simulations. This study tells us that the turbulence gravitational wave is going to be expressed by a broken power law, and we know exactly from the simulation what are the values of this broken power law. So that's what we did. And what we found is that there is a beta dependence threshold of the gravitational wave amplitude, above which we can recover this degree of polarization, which actually what implies in 2 words is that if tomorrow I can confirm that there is a polarized gravitational wave signal, I may be unable to deduce the degree of polarization. In other words, there are 2 relevant stochastic gravitational wave backgrounds. A lower one, which is necessary to confirm the presence of a polarized signal, a higher one, which will allow me to estimate the degree of polarization and then go back to put constraints on the particle physics model or whichever, I mean, usually these models of cosmology come from particle physics, which is going to induce the polarization in my stochastic background. Now, the stochastic background can also tell us things about beyond GR, beyond general relativity, because in alternative theories of gravity, we have extra polarization apart from the plastic cross of GR. Now, if we are trying with the transient gravitational wave signals to be able to detect this extra polarization, then the current generation of detectors, their position, and their orientation, in other words, and the limited number of interferometers we have cannot allow us to do this study. But a few years back, we proposed a Bayesian method to detect and characterize the polarization of the stochastic background. This method has been used in O2, has been used in O3, and the answer which we have is that there is no evidence for non-GR polarization. The non-detection of the scalar and vector polarized gravitational waves is consistent with the predictions of general relativity. Now, let me move briefly in something else. So far, I talked about the background. Now, to the first approximation, the stochastic background is assumed to be isotropic in the same way like the cosmic microwave background, the relic photons of the Big Bang. But an anisotropic distribution of my source, which is going to give me the stochastic background, is going to give to anisotropes the stochastic background in the same way like for the CMB. In the CMB, you study the two-point correlator of the temperature fluctuations. In the gravitational waves, I can go and study the two-point correlator of the omega GW fluctuations. And I can produce maps of the sky in the same way like people do in the CMB using gravitational waves. In that way, I'm going to have an independent way of studying the large-scale structure of the universe.
3 minutes.
Yes, thank you. So assuming an unpolarized Gaussian stationary stochastic gravitational wave background, I can go and write down the quadratic expectation value of the strain across different directions in the sky, which are given by theta, and different frequencies, which are given by f. And then we assume that we can factorize the gravitational wave strain power in with two terms, one which depends only on the frequency and one which depends only on the direction. Now, we have checked that this assumption, to factorize it like that, is correct as long as I am within the frequency band of LIGO Virgo. And then what we do, we write the cross-correlation spectra of our detectors I and J in terms of a set of basis functions, which I'm going to label by mu. Now, depending whether I have a spherical harmonic decomposition, which is actually the one that reconstructs the harmonic coefficients of the gravitational wave power on the sky and can identify extended sources with a rather smooth frequency spectra, then in that way, the harmonic basis that we're going to use is the LM that we are familiar, at least whoever of us has been working with, for the cosmic microwave background. If we do a broadband or a narrow band radiometer analysis, then we use the pixel basis. So here I give you a snapshot of the directional searches paper of the LIGO Virgo Kagra collaboration, where you can see for different values of alpha, 0 for cosmological background, 2/3 for CBCs, 3, which is more about supernova, upper limit sky maps of the gravitational wave energy flux from on the top, search from point-like sources, and the bottom from extended sources. Now there is a problem here. Well, not really a problem, but someone can say how good the resolution could be. And there is the diffraction limited angular resolution of the sky, which is going to limit it. What is the smaller angular separation, the smaller resolution I can have, which depends on the distance between my detectors and the sensitivity and the most sensitive frequency of my interferometer. And this is going to set up, depending on the value of the alpha, the maximum multiple N. And as you can see, for instance, for CBCs is 4, is rather small. So if I consider compact binary correlations, then the constraint that you can put for this two-point correlation that we are going to have is 1.9 times 10 to the minus 9, okay? Now, if I go to do a theoretical analysis, then you can see that we can go 3 orders of magnitude better. So there is a gap that we can we should actually to make it as smaller as we can as time goes on, and this could be done with more interferometers and better kind of sensitivity. Here I show you, as I showed you a few slides before, a map of the sky for the CMB. Here I show you a map of the sky, which we make by taking the Millennium Catalog and by studying what will be the anisotropies in the gravitational wave background from the compact binary coalescence. Now, there is a catch here that one has to keep in mind. There is a good thing, which is that the anisotropies are largely insensitive to the BBH population. But there is a problem which comes from the finite number of the compact binaries per observational time, the finite number of galaxies, and the one universe we have, the cosmic invariance, and this introduces a scale invariance bias term, which actually can mask the real anisotropy. So recently, I mean, not actually recently, a couple of years back with a student of mine, Alex Jenkins and Joe Romano, we proposed a new minimum variance unbiased estimator, which now we plan to incorporate for the next analysis of the LIGO Virgo data, and this probably can give us the more precise way of evaluating the anisotropies. If I do the similar exercise for cosmic strings, and again, I show you a map of the sky, and again, we have the same result. It is insensitive to the particular model for the loop distribution, and again, the theoretical studies can give a better constraint than the data we have so far. Now, I cannot retain myself not to jump into something else which is not that relevant for stochastic background, but I would like to advertise how one can put constraints on alternative theories of gravity and as well on even quantum gravity by using gravitational waves. So just allow me a couple of transparencies.
Sorry, Mary, I will have to be strict here because we've only got 2 minutes, and then
I can say that in 2 minutes. So lovely. My first minute is that in GR, gravitational waves far from their source propagate along null geodesics with energy and momentum, which are related with this dispersion relation. If we have an extension of GR, then we might have modifications. The modifications have been actually given in terms of this phenomenological term that you can see here in red. So a non-zero parameter A is going to manifest in the data as a frequency-dependent dephasing of the gravitational wave signals, which you can see like that. And it's going to build up as the gravitational waves propagate toward there. So depending on whether you have massive gravity, Korab ellipses, extra dimensions, whatever, there will be a different value for this quantity, and constraints have been put from the data from the catalog with all the transits data that we have. And the most important is to put a constraint of the mass of the gravity. The last thing I would like just to highlight very briefly is, the dimensional flow, which is the scale dependence of the dimensionality of space-time, is a feature which is shared by many theories of quantum gravity. So here, what I saw is the luminosity distance of gravitational waves, which propagate in a dimensionally changing space-time in quantum gravity. And you are going to have the strain, which is measured by your interferometer, and the luminosity distance, which is measured by the optical counterpart of the standard siren. In GR, the luminosity distance of gravitons and photons is the same. But if you have a non-GR theory, then these things are going to be different. Now, everything depends whether your theory has one scale or more than one scale. If there is one fundamental scale, then this L star is the Planck scale. This expression is correct, and this quantity small gamma here is the scale at which quantum gravity correction are important. If this L star is a mesoscopic scale, then this one, it is correct only in the infrared regime, and then this parameter gamma, it is the scale at which contribution to GR are small but not negligible. We have seen that if you want to put a constraint in the case that exists a counterpart of the standard siren that can be done only if the gamma mesoscopic is bigger than the gamma UV. Then you go in the literature and you read what are the values for these two parameters. For group field theory, spin forms, loop quantum gravity, causal dynamical triangulation, stellar gravity, string theory, whatever you want. And what we have found, this exists in the literature, what we have found is that with a standard siren, we can put a constraint only on group field theory, spin form, and loop quantum gravity. This does not mean that these are the correct theories, but does mean that there are these three candidates for quantum gravity, which could be tested and constrained with the standard siren. And I leave you with my conclusions. Thank you very much.
Thank you very much, Mayuri, for a really comprehensive and clear talk. We are out of time, so I will postpone the questions, but if anybody has questions for Professor Sakellariou, please put them in the chat, and she'll be glad to answer them, I'm sure. The next speaker and the last speaker of the session is Osamu Situ. And if I can get you, Osamu, to share your screen, please.
Okay. Oh. Okay, can you see my screen?
Yes, perfect.
Okay. Okay, so today I'm going to talk about this kind of theoretical thought and also cosmological gravitational source. So that is cosmological first order phase transition that happened after the inflation, but before Big Bang nucleosynthesis. And and in this talk, I'm going to talk about the relation between this gravitational wave background and possible probe of neutrino mass generation mechanisms. Okay, and then those are references just in case. So I spent recent years on this subject. We submitted these 3 papers, and those are collaborators. Okay. Yes. All right. So then let me begin with introduction. So I guess I don't need to talk about this first equation. So this is so gravitational wave is wave propagation mode of gravitational wave. So we have 2 polarization, plus and cross. Well, so those gravitational wave could be produced by this energy source T mu nu, and with some reason, if this T mu nu is excited, then that could be a source of generation of gravitational waves. So as far as cosmological observation gravitational wave is concerned, so there are several possibilities. One is inflation and preheating, so that sequence of the possible sources. Yes, so topological defects and phase transition. So today, I'm going to talk about this cosmological phase transitions. Okay, so so in cosmological phase transition, so it is said if this is a strongly first order phase transition, then this could produce that transition produces gravitational waves. So in terms, so this phenomena can be described in terms of scalar potential in our universe. So this is certain scalar field. Vertical axis shows this as potential energies. So then, so this is a so yeah, and well just right after the inflation and the heating was completed, then our universe becomes very hot, right? Becomes as a fireball, as Gamow said. And as the temperature cooled down, then due to this thermal correction to the scalar potential is diminishing. And in certain time, so this at the time, at the high temperature, we have vacuum or minimum for the scalar field phi at the origin. But so as temperature decreases, so then this scalar potential is deformed as like this. So then if scalar potentials deformed as like this at a certain temperature, so this shape of scalar potential is the potential which is responsible for first order phase transition. That is because now you can easily see. So scalar field is a kind of order parameter to describe the phases, right? So then now here we have this 1 minima and 2 minima. This is true minima actually. Then there's a first vacuum. And since this phi is the order parameter, but this here we have the gap between in those phases and the order parameter. So then this is the definition, right, of first order. So this order parameter has a certain gap from the one phase and to another phases. So in such a case, if phase transition proceeds like this, then there is a certain area in your universe. All area was initially false vacuum. So, but some area started to transit into true vacuum or lower vacuum, something like this. So then this just as a water bubble is produced when water is evaporated. So there is a true vacuum surrounded by true vacuum bubble surrounded by false vacuum. So then so this bubble formation and the two bubbles collide, or then some fluid dynamics characterized by sound wave in the fluid, or turbulence of the fluid. So those could be sources of gravitational wave production in cosmological phase transition context. Okay, so today I'm going to anyway, I'm interested in phase transition. So then let's see what transition I'm going to focus on. So okay, so this is this subtitle. So which phase transition we are going to discuss. So then today, so this is my motivation. So as we know, so there's several evidences, convincing evidence, which tells us our neutrino has a mass, very tiny, but there's non-vanishing mass. And this this is confirmed by lots of neutrino oscillation phenomena. Anyway, so this is and also evidence of existence of some new physics beyond the standard model of particle physics. And the most kind of simplest and economical explanation of this neutrino oscillation is there is a mass of neutrino, and that mass is actually its mass of neutrino is not allowed in the standard model of the particle physics. Therefore, we have to extend standard model. The simplest extension is this so-called seesaw mechanism by introducing right-handed Majorana neutrinos. This was proposed about more than 20 years ago. Okay, so this is the kind of trick. So we know neutrino is a very strict sense standard model predict zero mass. But once if we introduce right-handed neutrinos, we can write down this kind of mass matrices. Then if we diagonalize it, it naturally explains why neutrino mass is small, because if we assume this right-handed neutrino mass is heavy, so small number or a small number divided square divided by large number, that is small number. So therefore, this is what somehow widely accepted as a nice explanation about smallness and also origin of neutrino mass. So the next question would be where these mass terms come from. Of course, we can put by hand, but well, so many of us or some of us are not so happy with just introduced by hand. And also, this is also this will be a question of the particle physics, but that is also important key for cosmological discussion. That is because this scale of right-handed neutrino mass is directly related to the mechanism of matter antimatter generation in our universe. Or that is shortly called baryogenesis. So anyway, in order to identify baryogenesis mechanisms to guess mass scale of right-hand neutrino is important. Okay, so and then this is oh, maybe I shouldn't do so slow. So this is a kind of what we know currently: weak scale electroweak symmetry breaking and some scale. Okay, so then this is ground unification. Then this is we guess there must be certain phase transition that is responsible for mass generation of right-hand neutrino. So then today I focus on this symmetry breaking. And as an example, I focus on so-called U1 B minus L symmetry breaking. Well, so U1 is just normal U1 abelian symmetry, and B minus L here B is a baryon number and L is a lepton number. So we can this differences between baryon number and the lepton number can be enlarged as a gauge symmetry. This was originally global symmetry in the standard model, though. But this is very natural because this symmetry is already exists in the standard model. And this is anomaly free, so that means healthy. And this has a great prediction. That is, this right-hand neutrino should have 3 generations. And also this is very ground unified theory friendly extension. I'll come back to this ground unification theory in the end of my talk. Okay, so and maybe I don't have so much time to talk in detail, so therefore just briefly show you the existence or kind of prove this U1 B1 L breaking can produce large enough of gravitational wave by first order phase transitions. So then, so key point of first order phase transition is this actually this small bump here. This is important because I mean, so this bump separate true bucket and false bucket, right? And so therefore, actually, how this bump is produced is a kind of secret of how we can make phase transition to be a first order. And two possible sources. I mean, in terms of how to generate this bump. One is a tree level. I mean, classically, we should prepare this. We prepare this bump, or quantum collection generate this small bump. Then that could cause this first order phase transitions. So then depends on the cases. Actually, yeah. So therefore, you have to classify the 2 cases. And then so I draw this. I wrote 2 papers, but anyway, and this I will skip here. So this is the result. So anyway, so these there is 2 cases, but actually final result is not that much different. So therefore, I just summarize one plot here, and then here so I can convince you here. This first order phase transition. This colored line is a kind of theory prediction. Of course, we have to pick certain parameters, but anyway, if we choose certain good benchmark points, then those green, blue, red is a theory prediction. Then this black line with a name is those experiments expected sensitivity. Okay, so then those many benchmark points can be probed by those LISA, BBO, DECIGO, CE, Cosmic Explorer. And this is a parameter dependence of this amplitude and frequency of gravitational waves. So anyway, yes. So this U1 B1 L symmetry breaking with certain parameter choice. This phase transition can produce a large enough or a large amplitude of gravitational wave, which could be potentially detected by future experiments. And last couple of slides. So as I said, so this U1 B minus L is a ground unified theory friendly framework. So therefore, here, last slide, I want to show you how this U1 B minus L breaking is matched with ground unification. So ground unification is kind of more good. What's how to say? Kind of just paradigm, right? We want to understand any different interaction in a beautiful or single way, right? So we unify electromagnetic force and weak force and unify electroweak force, so on and so forth. So then this ground unification is a theory which could unifiedly explain strong and weak and electromagnetic forces. And this is a bit too much particle physical, so therefore let me skip here. And this is how also just particle physical detail. But anyway, this is the existence proof for you. There's a way to make it this extra U1 B minus theory to embed inside SO10 model. And so this is the approach. So depending on this U1 symmetry breaking scale, so this resultant gravitational wave spectrum is varied as like this. And also, next slide I want to show you is so this number or this bracket or left number is the value of Yukawa coupling, which is responsible to right-handed neutrino mass. So therefore, this is so this size is proportional to the mass of right-handed neutrino. So therefore, if we vary this number, then if resultant spectrum is changed, so that means this is a kind of imprints of right-handed neutrino mass into gravitational wave spectrum. Then, as you can see, if we vary from green to blue to purple, then the size, amplitude, or peak frequency changes as like this. So therefore, in principle, we can find some imprints of a mass scale of right-handed neutrino inside gravitational wave spectrums. And well, so this is a summary of what I talked so far, and I will stop here. Thank you very much.
Thank you very much, Dr. Seto. Questions? We have 2 or 3 minutes for questions, so I might, while we're waiting for any blue hands, if I can ask a naive one, please. These phase transitions that you're relying on, is there other evidence for their existence, or can we only check their existence through these gravitational wave?
Well, yes. How to say? That depends on actually the scale of the symmetry breaking. So the scale I focus on this talk was a relatively low scale. So therefore, yeah, we only have this imprints only on gravitational wave. If scale is larger, then that could produce cosmic strings. But so that is just a choice or just a symmetry, just parameter dependent. So high scale that can produce cosmic strings, and then there's not so much. In such a case, we cannot we cannot detect gravitational wave from phase transition. But in our case, we somehow, as you can see this slide. So our symmetry breaking was I choose about PeV or 10 TeV or so. Then so this in this case this range becomes below lower frequency as those experiments can detect. In such a case, gravitational wave from cosmic string is very negligible. So in this case, this gravitational wave, this is only way.
I see. Thank you. That's very clear. I would just say the session may cut out at any point now. There is a question you might want to answer briefly or somewhere in the chat from Lucy Strang. How do the scales
okay, LHC limit is about this scale is about few TeV. And let's see, it's actually, okay. So this green line corresponds to lower bound from the LHC for TeV. So therefore, less than for TeV, so this is the current lower bound satisfied from the LHC.
Understood. Okay, great. Well, look, we will finish there. We're out of time. I just want to say 3 very quick thank yous. Firstly, to the audience, very warmly, thank you for attending and making it a great session. Secondly, thank you to all the speakers for great talks and for sticking to time. And thirdly, thank you to the co-hosts, Meg Milhouse and Lucy Strang, for staying online for the duration. Our next GW1 session is tomorrow, and it's a short session starting in the 9:30 block. So perhaps we'll see you then. All the best, everybody. Bye-bye.